Look up at the night sky, and you'll see more than just scattered points of light. You're gazing into a cosmic tapestry woven with mysteries older than time itself. Among those shimmering specks lie star clusters, celestial families bound by gravity, hiding secrets that defy our understanding of the universe. Some of these clusters glow with the light of newborn stars, while others whisper tales of ancient stellar graveyards. But here's what's truly mind-blowing. No matter how much we learn, these glittering gatherings keep surprising us with discoveries so strange. They challenge everything we thought we knew about space. Take globular clusters, for example, dense, spherical swarms of stars that orbit galaxies like cosmic bees around a hive. Scientists once believed these clusters were peaceful, orderly neighborhoods where stars aged gracefully. Then came the shocking revelations. Some clusters harbor rogue black holes, lurking unseen and rewriting the rules of stellar evolution. Others spit out hypervelocity stars, flinging them across the galaxy at speeds so insane they escape the cluster's grip forever. And then there are the Blue Stragglers, stars that somehow cheat death, appearing younger and brighter than their siblings, as if cosmic magic is at play. This is just the beginning. Over the next 50 discoveries, we'll unravel the enigmas hidden within these stellar communities. We'll meet star clusters that shouldn't exist, ones that vanish without a trace, and even clusters that might be hiding alien megastructures. Each revelation peels back another layer of the universe's grand puzzle, reminding us that space is far weirder and more wonderful than we ever imagined. So buckle up. By the time we're done, you'll never look at the night sky the same way again. Deep within the star cluster Messier 5, astronomers stumbled upon a cosmic predator lurking in the shadows, a pulsar known as the Black Widow. This isn't just any spinning neutron star. It's a celestial vampire, methodically devouring its companion in a dance of death that defies the peaceful image of star clusters. Imagine a spider spinning its web, but instead of silk, this pulsar blasts its partner with searing radiation and particle winds, stripping away layers of stellar material bit by bit. Over millennia, the companion star, once a vibrant sun, is reduced to a withered husk, its mass siphoned away to feed the pulsar's relentless spin. What makes the Black Widow pulsar even stranger is the sheer violence of this process. The pulsar doesn't just quietly absorb material. It bombards its victim with enough energy to create shockwaves that glow across multiple wavelengths, from radio waves to X-rays. It's like watching a star being slowly sandblasted by a cosmic fire hose. And here's the eerie part: this isn't some rare fluke. Astronomers have found dozens of these systems, suggesting that star clusters might be crawling with similar stellar predators, rewriting our understanding of how binary systems evolve. The implications ripple far beyond this one pulsar. If these vampiric relationships are common, they could explain why some star clusters seem to lose their smaller stars over time. It's a dark twist on stellar evolution, one where the survivors aren't the brightest or the biggest, but the most ruthless. Even more unsettling, the Black Widow's feast may eventually leave it alone, a solitary predator drifting through the cluster, hinting that these cosmic killers might be far more numerous than we ever suspected. Among the aging stars of ancient globular clusters, astronomers keep finding cosmic imposters, brilliant blue stars shining far too brightly for their supposed age. These are the Blue Stragglers, celestial rebels that refuse to fade away gracefully. Picture a retirement home where some residents inexplicably look and act like teenagers. That's the baffling scenario playing out in clusters billions of years old, where Blue Stragglers burn hotter and bluer than their ancient neighbors, like fresh paint splashed on a faded masterpiece. So how do these stars cheat time? The leading theory involves stellar collisions, cosmic pile-ups where two stars smash together, merging their fuel and reigniting like a phoenix rising from the ashes. In the crowded core of a globular cluster, stars dance perilously close, and when gravity orchestrates a head-on crash, the result is a rejuvenated star with a fresh supply of hydrogen, burning with youthful vigor. Another possibility involves vampiric binary systems, where one star siphons gas from its companion, puffing itself up while leaving the donor star drained. But the strangest twist, some blue stragglers seem to form without any obvious trigger. In the cluster NGC 6760, astronomers found these blue rebels drifting alone, far from the dense stellar traffic where collisions should occur. This suggests there might be unknown processes at work, perhaps secret stellar cannibalism or even exotic physics we haven't yet imagined. Whatever the cause, blue stragglers force us to rewrite the rules of stellar aging, proving that in the cosmic dance of star clusters, some partners never grow old gracefully, they just steal a second act. The star cluster Omega Centauri, a glittering metropolis of millions of stars, hides a population of celestial fugitive stars racing away at speeds so blistering they defy the cluster's gravitational grasp. These aren't just fast-moving stars, they're cosmic escape artists flung into the void with enough velocity to leave their birthplace behind forever. Picture a fireworks finale where some sparks rocket sideways at impossible angles, vanishing into the night while the rest fade gently. That's the spectacle unfolding in Omega Centauri, where gravitational chaos turns ordinary stars into intergalactic outlaws. So what catapults these stars to such extreme speeds? One leading culprit lurks in the cluster's crowded core, a game of gravitational pinball. When stars swing too close to a binary system or a hidden black hole, the encounter can slingshot them outward like a stone from a sling. These gravitational kicks, sometimes exceeding 1 million miles per hour, are so violent they essentially evict the star from its stellar neighborhood. Another explosive possibility, supernovas. If a massive star detonates near a companion, the sudden loss of mass can send the surviving star hurtling away, unshackled by the blast's recoil. But the real shocker came when astronomers mapped these runaway stars and realized some weren't just fleeing, they were launched in coordinated directions, as if the cluster itself had spat them out in bursts. This suggests Omega Centauri might have endured catastrophic events in its past, like a close brush with another cluster or the sudden collapse of its core. The runaway stars become celestial breadcrumbs, tracing violent chapters in the cluster's history that we're only now deciphering, even more intriguing. A few of these escapees are hypervelocity stars streaking so fast they could eventually break free of the Milky Way entirely, becoming lone wanderers in the intergalactic void. These stellar fugitives force us to rethink how star clusters evolve. Far from static collections, they're dynamic arenas where gravity writes its own rules, and sometimes those rules include ejecting their brightest members into the cosmic unknown. Every runaway star carries a story of chaos, a moment when the cluster's delicate balance tipped into pandemonium. And as we study their trajectories, we're not just tracking stars, we're reconstructing the hidden upheavals that shape the universe's most crowded stellar neighborhoods. Somewhere in the vast cosmic ocean, a star cluster drifts like a ghost ship defying the very laws that govern the universe as we know it. Meet NGC 1052 DF2, a celestial anomaly where the expected anchor of dark matter is conspicuously absent. This isn't just a missing piece of the puzzle, it's a fundamental challenge to our understanding of how galaxies and clusters form. Imagine building a skyscraper without steel beams. That's the level of impossibility we're dealing with here. Yet this cluster exists, shining brightly with stars but lacking the invisible glue that should hold it together. The discovery sent shockwaves through astrophysics because dark matter isn't just a minor component of the cosmos, it's the scaffolding. Most galaxies and clusters are thought to be nestled within vast halos of this mysterious substance, whose gravity keeps them from flying apart. But when astronomers measured the motions of stars in NGC 1052 DF2, they found something bizarre. The stars were moving so slowly that without dark matter's gravitational pull, the cluster should have disintegrated eons ago. It's like finding a car speeding down the highway with no engine somehow. Against all logic, it's still running. Debates erupted instantly. Could our instruments be wrong? Did some catastrophic event strip away the dark matter? One radical theory suggests the cluster might be the aftermath of a galactic collision, where the violent encounter ripped dark matter away like a cosmic tide. Others propose that dark matter interacts with itself in ways we don't yet understand, creating invisible pockets where it simply vanishes, the most unsettling possibility. That our models of dark matter are incomplete or worse, fundamentally flawed. What's truly fascinating is how this cluster refuses to play by the rules. While most cosmic structures follow predictable patterns, NGC 1052DF2 dances to its own rhythm, forcing scientists to reconsider decades of assumptions. If dark matter can go missing here, where else might it be hiding or not hiding? Every star in this defiant cluster is a silent challenge, whispering that the universe still holds mysteries we're only beginning to grasp. And as telescopes peer deeper into the void, one thing becomes clear: the cosmic rulebook is far from finished. Globular clusters were once considered cosmic retirement homes, peaceful collections of aging stars where black holes shouldn't exist, let alone thrive. That assumption shattered when astronomers peered into the heart of Messier 15 and found a gravitational monster defying the rules. Hidden within this ancient cluster of hundreds of thousands of stars lies an intermediate mass black hole, a mysterious class of celestial predator that shouldn't theoretically form in such environments. This isn't just an oddity, it's a cosmic paradox forcing us to rewrite the story of how black holes grow. Intermediate mass black holes occupy the elusive middle ground between the small stellar mass black holes born from collapsing stars and the supermassive giants lurking in galactic centers. Scientists have long debated whether they even exist, but Messier 15's hidden beast, weighing in at roughly 2,000 times the mass of our Sun, proves they're not just real but lurking where we least expect them. The discovery sent shockwaves through astrophysics because globular clusters lack the dense gas clouds needed to feed a growing black hole. So how did this one get so big? One theory suggests it's a relic from the cluster's violent youth, formed when multiple smaller black holes collided and merged over billions of years, like a snowball rolling through cosmic history. But here's where it gets stranger. The stars near Messier 15's core whip around at dizzying speeds, their orbits betraying the black hole's presence like leaves caught in an invisible whirlpool. These stellar motions reveal a gravitational grip so strong it can't be explained by visible matter alone. Even more puzzling, this black hole isn't actively feeding, it's dormant, a silent titan biding its time. That contradicts everything we know about black holes in dense stellar environments, where constant collisions should keep them well-fed and detectable. The implications ripple far beyond this one cluster. If intermediate mass black holes are common in globular clusters, they could be the missing link in understanding how supermassive black holes form in galactic centers. Picture them as cosmic stepping stones, growing through mergers until they become the universe's most dominant gravitational forces. Or consider an even wilder possibility. These hidden giants might be the remnants of primordial black holes, forged in the chaotic aftermath of the Big Bang itself. Messier 15's silent predator doesn't just challenge our understanding of star clusters, it forces us to rethink the very origins of black holes and their role in shaping the cosmos. And yet, the biggest question remains unanswered. How many more of these lurking giants are out there, rewriting the rules in plain sight? Every globular cluster we study now feels like a cosmic detective story, with the next clue hidden in the dance of ancient stars. One thing's certain: the universe loves proving us wrong, and its surprises are far from over. In the constellation of Antlia, astronomers uncovered something that shouldn't be there, a star cluster so faint it's practically invisible. This ghostly gathering of stars, officially named Antlia 2, doesn't glow like its cosmic cousins. Instead, it lurks unseen, detected only by the subtle tugs it exerts on nearby stars, like a shadow passing through a crowd. What makes this discovery so unsettling isn't just its near invisibility. It's the realization that clusters like this might be far more common than we ever imagined, hiding in plain sight while rewriting our understanding of dark matter's role in the universe. Most star clusters announce their presence with bright young stars or dense collections of ancient suns. Antlia 2 does neither. Its stars are spread so thinly that if you were floating among them, the night sky would appear nearly empty. Yet this sparse arrangement defies logic. Without enough visible mass to hold itself together, the cluster should have dissolved into the cosmos long ago. The only explanation, an enormous halo of dark matter far larger than the cluster itself, acting like an invisible scaffold keeping these scattered stars bound together. The problem: our current models suggest globular clusters like Antlia 2 shouldn't have this much dark matter at all. The implications are staggering. If dark matter can cling to fragile clusters in such unexpected ways, it might mean we've been overlooking an entire population of cosmic ghosts, structures too faint to see but massive enough to influence their surroundings. Some researchers speculate these shadowy clusters could be failed galaxies, objects that started forming eons ago but never gathered enough gas to ignite vibrant stellar nurseries. Others suggest they are the remnants of violent galactic collisions, torn apart and left to wander as cosmic phantoms. But the real mystery lies in the dark matter itself. Antlia 2's halo is oddly puffed up, less concentrated than theories predict. This could mean dark matter behaves differently in these environments, perhaps interacting with itself or other forces in ways we haven't accounted for. Or worse, it might hint that our grasp of dark matter's nature is flawed, that we're missing a fundamental piece of the puzzle. What's certain is that Antlia 2 isn't alone. New surveys are revealing other ghostly clusters, each one a whisper from the cosmos, reminding us that the universe is still full of secrets. These faint, dark matter-rich structures could be the missing link between dwarf galaxies and star clusters, a hidden chapter in the story of how the cosmos assembles itself. And as telescopes grow more sensitive, we're left wondering, how many more of these phantoms are out there, quietly shaping the universe from the shadows? Floating in the void between galaxies, a lone star cluster drifts like a cosmic castaway, untethered, unbound, and utterly mysterious. This is the intergalactic wanderer, officially known as NGC 2419. A shimmering island of stars adrift in the emptiness between the Milky Way and the Andromeda Galaxy. Unlike most clusters which orbit galaxies like moons around a planet, this one answers to no galactic master. It exists in the intergalactic wilderness, a place so vast and empty that its very presence defies explanation. How does a star cluster end up so alone? The leading theory is as dramatic as it is violent, a galactic collision. Billions of years ago, two galaxies may have clashed, their gravitational chaos flinging this cluster into the abyss like a stone hurled from a slingshot. Another possibility is that the cluster formed in the turbulent wake of such a collision, born from gas ripped free during the encounter and left to condense into stars far from any galaxy. But here's the twist: when astronomers studied the Wanderer's chemistry, they found stars older than many galaxies themselves, suggesting this cluster might be a primordial relic, a surviving fragment from the universe's earliest days. The real puzzle isn't just how it got there, but how it survives. Without the protective embrace of a galaxy, the cluster is exposed to the harsh tides of intergalactic space, where stray gas clouds and dark matter currents could tear it apart. Yet somehow it endures. Its stars cling together with a tenacity that baffles scientists, as if bound by an unseen force beyond gravity. Some researchers speculate it could be encased in a cocoon of dark matter, an invisible shield we can't yet detect. Others wonder if it's just the first of many, that the cosmos might be littered with similar rogue clusters, drifting unseen between the galaxies. the intergalactic wanderer forces us to rethink what we know about star formation and survival. If clusters can thrive in the void, then the universe's stellar communities might be far more diverse and far stranger than we ever imagined. Every flicker of light from this lonely cluster carries a question. Are we looking at a cosmic accident, a forgotten relic, or a hint of something even more extraordinary? As telescopes probe deeper into the darkness between galaxies, one thing becomes clear: the universe still has secrets to spill, and some of them are floating right in front of us, waiting to be found. Nestled in the constellation Serpens lies a celestial treasure chest, the star cluster Messier 5, home to some of the most bizarre stellar oddities in the cosmos. Among its ancient suns, astronomers have identified a rare breed known as carbon stars, their atmospheres so rich in carbon atoms they could theoretically crystallize into diamond-like structures. Imagine a star where the conditions are so extreme, the carbon in its outer layers condenses into cosmic gems as it cools, a literal diamond factory floating in space. These carbon stars defy the usual stellar chemistry. Most stars fuse hydrogen into helium, then heavier elements like oxygen and carbon. But these outliers have dredged up so much carbon from their cores that it dominates their atmospheres. When such a star nears the end of its life, shedding its outer layers, the carbon can cool and solidify into graphite, or under the right pressure, even diamond. In Messier 5, this process might be happening on a staggering scale, with entire stellar atmospheres potentially sprinkled with microscopic diamonds. What makes this cluster's carbon stars particularly intriguing is their age. Messier 5 is over 12 billion years old, meaning these stars have been stewing in their own carbon-rich soup for eons. The slow burn of time allows for exotic chemical processes we rarely see elsewhere. Some models suggest that as these stars exhale their carbon-laden winds, the material could coalesce into solid particles long before dispersing into space. Picture a dying star coughing up diamond dust into the void, a final, glittering farewell. But here's the twist: we've never directly observed these diamond structures. The evidence is circumstantial, inferred from the star's chemical fingerprints and the extreme conditions in their atmospheres, yet the physics checks out. In lab experiments, carbon crystallizes into diamonds under high pressure and temperature conditions eerily similar to those in the outer layers of these aging stars. If even a fraction of the carbon in Messier 5 stars has solidified, the cluster could contain more diamond-like material than all the precious gems ever mined on Earth. The implications stretch beyond cosmic bling. These carbon-rich stars are time capsules, preserving the chemical legacy of the early universe. Their existence hints at how elements crucial for life, carbon, the backbone of organic molecules, were scattered across the cosmos. And if diamond formation is possible here, it might be happening in other ancient clusters too, rewriting our understanding of how stars enrich the universe with solid matter. So while we can't yet mine these stellar diamonds, their very possibility reminds us that the cosmos is far stranger and more dazzling than fiction. Messier 5's glittering secrets challenge us to rethink not just how stars die, but how the universe itself turns stardust into something truly extraordinary. Tucked away in the outer reaches of our galaxy, astronomers have uncovered a celestial relic that could rewrite the cosmic family tree of star clusters. Known as E3, this ancient gathering of stars doesn't fit neatly into either the globular or open cluster categories. It's something in between, a cosmic missing link that challenges everything we thought we knew about how these stellar families form. Picture a biological hybrid like the platypus of the animal kingdom, defying classifications with its mix of unexpected traits. That's E3, a cluster that looks too loose to be globular yet too old and dense to be a typical open cluster, forcing us to reconsider the origins of all star groups. What makes E3 so revolutionary is its age, roughly 12 billion years old, dating back to when the universe was just a toddler. Most clusters that ancient are tight, spherical globulars, but E3 stars are scattered more like a modern open cluster, as if it froze in time before fully compacting. One theory suggests it might be a failed globular, born during an era when the ingredients for cluster formation were different. Back then, the universe hadn't yet built up heavy elements like iron and silicon, which act as cosmic glue in later star formation. Without them, E3 may have struggled to pull itself together as tightly as its globular cousins. But the plot thickens when you study its stars. Unlike most globular clusters, where stars are nearly identical in age and composition, E3 hosts a surprising mix. Some stars are primordial, barely changed since the Big Bang, while others show traces of heavier elements. This suggests the cluster might have cannibalized younger stars or gas clouds over eons, stitching together a patchwork history. Even stranger, its current shape hints at violent encounters, perhaps a close brush with a galaxy's gravitational tides that stretched it into its current hybrid form. The implications ripple far beyond this one oddball cluster. If E3 is a bridge between cluster types, it could reveal how early universe conditions shaped star formation. Picture it as a cosmic fossil, preserving a transitional phase most clusters outgrew. Some astronomers even speculate that clusters like E3 were once common, but most merged or dispersed, leaving this one as a rare survivor. That would mean our current census of clusters is incomplete, missing an entire class of objects that could hold secrets about the universe's chaotic youth. As telescopes probe deeper into the galactic outskirts, E3 stands as both a puzzle and a Rosetta Stone. Its very existence suggests that the early universe experimented with cluster designs we've never imagined, and that some of those experiments might still be hiding in plain sight. Every star in this ancient gathering whispers a question. Are we looking at a cosmic accident or the key to understanding how all star clusters evolved? One thing's certain: the more we study it, the more the universe reminds us that its history is written in exceptions, not just rules. The serene image of star clusters as perfect spheres floating through space gets violently torn apart when gravity decides to paint with a darker brush. Enter tidal tails, luminous ribbons of stars stretched across the cosmos like celestial taffy, revealing the hidden brutality of galactic encounters. These aren't delicate cosmic streamers, they're the aftermath of gravitational warfare, where clusters collide with galaxies or pass too close to massive neighbors, and the resulting forces rip stars away in spectacular arcs. The process is as mesmerizing as it is destructive, turning orderly clusters into fragmented trails of light that can span thousands of light years. Take the cluster Palomar 5, a faint smudge of stars in the constellation Serpens. At first glance, it seems unremarkable until astronomers spotted its twin tidal tails, each stretching over 30,000 light years into the void. These tails aren't random debris, they're precise gravitational signatures, mapping the cluster's repeated encounters with our Milky Way's disk. Every time Palomar 5 plunges through the galactic plane, the tidal forces strip away stars like layers of an onion, leaving behind a glittering breadcrumb trail of its orbital history. What's eerie? The cluster's tails are asymmetrical, one significantly longer than the other, hinting at a past collision with a massive dark matter clump we can't even see. But tidal tails aren't just forensic records of violence, they're stellar nurseries in disguise. As stars are yanked free from their parent cluster, they carry with them pockets of gas and dust. In the relative solitude of these tidal streams, that material can collapse under its own gravity, sparking the birth of new stars. It's a cosmic irony. The same forces that tear clusters apart also create opportunities for rebirth. The tail of the Hyades cluster, one of the closest to Earth, contains young stars that shouldn't exist if the cluster had aged in isolation, proving that chaos and creation are two sides of the same celestial coin. The sheer scale of these structures defies imagination. Some tidal tails, like those of the Sagittarius dwarf galaxies, disrupted clusters, wrap around the Milky Way multiple times, forming a skeletal framework of stellar rivers in our galactic halo. Others, like the Monoceros ring, are so vast they were initially mistaken for separate galaxies. These tails challenge our definition of what a star cluster even is. Are they still bound families if their stars are scattered across light years? Or do they become something new, a transitional phase between clusters and fully dispersed stellar populations? Perhaps the most unsettling implication of tidal tails lies in their inevitability. Given enough time, every globular cluster orbiting a galaxy will succumb to tidal forces, slowly dissolving into these radiant streams. They're not anomalies, they're cosmic obituaries showing us the fate awaiting even the densest clusters. Yet in their dissolution, they gift us something remarkable, a way to map the invisible gravitational landscape of the universe. Every twisted tail whispers secrets about dark matter distributions, galactic collisions, and the delicate balance between gravity's grip and the universe's relentless pull toward entropy. For astronomers, these luminous scars are more than just pretty phenomena. They're dynamic laboratories. By studying how stars behave in tidal tails, we've uncovered clues about dark matter's granularity, the Milky Way's growth through cannibalizing smaller clusters, and even the potential for life-bearing planets in these nomadic stellar streams. After all, if stars can survive and even thrive in the gravitational no-man's land of a tidal tail, why couldn't their planets? The universe, it seems, refuses to let even its most violent processes go to waste, weaving destruction and creation into a single, shimmering tapestry. When astronomers first spotted a peculiar speck of light in the Fornax cluster, they assumed it was just another globular cluster until they measured its size. This cosmic oddball, now known as an ultra-compact dwarf galaxy, packs hundreds of millions of stars into a space barely larger than a typical star cluster, defying every rule about how galaxies should behave. Imagine cramming the entire population of a metropolis like New York City into a single high-rise. That's the level of density we're dealing with. But what really flips the script is how these objects behave. They're too massive to be mere star clusters, yet too small and dense to fit conventional galaxy models, existing in a cosmic gray zone that's rewriting astronomy textbooks. The discovery sent shockwaves through the field because ultra-compact dwarfs break multiple assumptions at once. Take M60 in the Virgo cluster, for example. It shines as bright as a small galaxy, but spans only about 120 light-years, roughly the distance between Earth and the nearby Pleiades star cluster. Inside that tiny volume, stars orbit at dizzying speeds, hinting at the presence of a supermassive black hole or unimaginable amounts of dark matter holding everything together. Neither explanation fits neatly into existing frameworks. If it's a black hole, it would be proportionally larger than those found in regular galaxies. If it's dark matter, its distribution defies all known patterns. Here's where classification systems start to crumble. Traditional galaxies, like our Milky Way, have distinct structures, spiral arms, halos, and central bulges governed by predictable dynamics. Star clusters, by contrast, are simpler, bound by gravity but lacking the complexity of true galaxies. Ultra-compact dwarfs smash this dichotomy. Some show chemical fingerprints of multiple stellar generations, suggesting they're the stripped cores of once larger galaxies, violently shredded by tidal forces until only the densest nucleus remained. Others, like the bizarre Omega Centauri, long considered a globular cluster, contain stars with wildly different ages and metallicities, a hallmark of galactic ancestry. The implications ripple far beyond semantics. If ultra-compact dwarfs are failed galaxies, they could reveal how cosmic environments shape galactic evolution. Picture these objects as cosmic island cores, surviving fragments of galaxies that ventured too close to larger neighbors and were devoured. Their existence might explain why we find so few mid-sized galaxies in the universe. They were all torn apart, leaving only their ultra-dense hearts behind. Alternatively, if they represent a distinct class of objects formed through some unknown process, they could point to gaps in our understanding of star formation itself. The hunt for answers is pushing telescopes to their limits. Recent observations of an ultra-compact dwarf named M59UCD3 revealed a central black hole weighing as much as 20 million suns, 4 times heftier proportionally than the Milky Way's own supermassive black hole. This discovery suggests these objects might be black hole delivery systems, transporting monstrous singularities across the cosmos through galactic mergers. Another study found that some ultra-compact dwarfs emit more X-rays than expected, hinting at violent stellar interactions or hidden pulsar populations unseen in normal clusters. What's truly humbling is how these discoveries expose the limits of human categorization. Nature doesn't care about our tidy definitions. It creates hybrids, outliers, and exceptions that force us to rethink our models. Ultra-compact dwarfs aren't just cosmic curiosities. They're living proof that the universe still holds entire classes of objects we've yet to understand. And with every new observation, they chip away at the boundary between cluster and galaxy, reminding us that the cosmos delights in blurring lines we once thought were absolute. Deep within the constellation of Draco lies NGC 6397, a ghostly gathering of stars that astronomers call the stellar graveyard. Unlike most clusters bursting with vibrant suns, this one is eerily dominated by the husks of dead and dying stars, white dwarfs, and neutron stars that whisper the final chapters of stellar evolution. Picture a city where the streets are lined not with bustling inhabitants, but with silent tombstones, each marking the end of a once glorious cosmic life. This cluster isn't just a collection of fading embers, it's a time capsule revealing what awaits nearly all stars, including our own sun, in the distant future. White dwarfs, the smoldering cores of stars like our sun, pepper this cluster like dim cosmic lanterns. Each one is a stellar corpse, having shed its outer layers in a spectacular planetary nebula phase before collapsing into an Earth-sized ember so dense, a teaspoon of its material would weigh as much as an elephant. But what makes NGC 6397 extraordinary is the sheer concentration of these remnants, so many that they outnumber the cluster's living stars. Their faint glow, barely detectable except with sensitive telescopes, tells a story of quiet decay over billions of years. Then there are the neutron stars, the cluster's more dramatic corpses. Born from the explosive deaths of massive stars in supernova, these objects are so dense, their atomic structure collapses into a sea of neutrons. A sugar cube-sized chunk would outweigh Mount Everest. Some of these neutron stars in NGC 6397 still pulse with radiation, spinning at dizzying speeds as pulsars, while others lie dormant, invisible except for their gravitational influence. The presence of both white dwarfs and neutron stars in one cluster offers a rare chance to compare how stars of different masses meet their ends. The real shock came when astronomers realized this graveyard is far hotter than it should be. The white dwarfs, though cooling, haven't dimmed as expected. One theory suggests that as stars die and shed mass, the cluster's gravitational balance shifts, causing surviving stars to get slingshotted outward in a phenomenon called mass segregation. This gravitational reshuffling could be injecting energy into the system, keeping the white dwarf stirred up like a pot that refuses to cool, another possibility. Dark, unseen companions, perhaps planets that survived their star's death or binary partners, are transferring energy and slowing the cooling process. But the most haunting revelation is what this cluster tells us about time. The oldest white dwarfs here have been cooling for nearly as long as the universe has existed, their temperatures serving as cosmic clocks. By studying them, astronomers can pin down the age of the Milky Way itself, confirming that our galaxy's earliest stars ignited over 13 billion years ago. Every faint gleam from these stellar remnants is a data point in the universe's autobiography, helping us piece together not just how stars die, but how galaxies grow old. NGC 6397 challenges our assumptions about cosmic mortality. It's not just a passive graveyard, it's a dynamic ecosystem where the dead influence the living. The gravitational echoes of these remnants may be sculpting the orbits of younger stars, and their expelled material could seed future generations of star formation. Even in death, these stars shape their corner of the cosmos, proving that the universe never truly lets anything go to waste. As telescopes peer deeper into this stellar necropolis, one truth becomes clear. The end of a star's life isn't an end at all, it's just another transformation in an endless cycle of cosmic rebirth. In the vast, seemingly barren outskirts of our galaxy, astronomers stumbled upon a cosmic miracle, a sparkling nest of newborn stars where no stars should exist. This infant cluster, known as object name pending, defies all expectations by thriving in a galactic no-man's land, a region so devoid of gas and dust that star formation was deemed impossible. Picture finding a bustling nursery in the middle of a desert. That's the level of astonishment this discovery has sparked. The cluster's youth is unmistakable. Its stars blaze with the blue-white intensity of stellar toddlers, some barely a few million years old, while the surrounding void offers none of the dense molecular clouds typically required to birth such stars. So how did this celestial maternity ward appear where theory says it shouldn't? One provocative explanation involves a galactic hit and run. Simulations suggest a rogue gas cloud, perhaps ejected during a long-ago collision between dwarf galaxies, could have been compressed by shockwaves as it plowed through the Milky Way's halo. Under just the right conditions, that collapsing gas might have ignited a single, desperate burst of star formation, a stellar lightning strike in the cosmic wilderness. But the plot thickens when you examine the stars themselves. Unlike most young clusters where stars share nearly identical compositions, this group shows bizarre chemical variations. A handful of stars are enriched with heavy elements like iron, hinting they formed from gas polluted by earlier supernova, while others are pristine, as if they condensed from primordial material untouched since the Big Bang. This duality suggests the cluster's birthplace wasn't just an empty void. It might have been a graveyard where the remnants of dead stars from an ancient, now vanished galaxy mingled with fresh intergalactic gas. The implications ripple far beyond this one anomaly. If young clusters can form in galactic wastelands, astronomers may need to rethink where and how they search for stellar nurseries. Current star formation models focus on spiral arms and dense nebulae, but object name pending proves the universe can craft stars in the most unforgiving environments. Even more tantalizing, this cluster's isolation means its stars evolve without interference from neighboring gas clouds or gravitational disturbances, offering a rare, pristine laboratory to study stellar infancy in its purest form. As telescopes scrutinize this cosmic contradiction, one thing becomes clear: the galaxy's rulebook is far from complete. Every flicker of light from this improbable cluster whispers that the universe still holds surprises in its quietest corners, and sometimes the most extraordinary things grow where we least expect them. In the dense stellar metropolis of the Globular cluster NGC 3201, astronomers uncovered a cosmic spectacle that defies the odds. A pair of black holes locked in a gravitational tango, circling each other in a dance that could last millions of years. This isn't just a scientific curiosity, it's a revelation that shatters long-held assumptions about how black holes behave in crowded star clusters. Conventional wisdom suggested that clusters like this should eject all but one black hole through gravitational interactions, leaving a single dominant predator. Yet here, two monstrous singularities coexist, rewriting the rules of celestial survival. The discovery came through an unlikely clue: the erratic flickering of a distant star. As telescopes tracked the motions of stars in NGC 3201, they noticed several orbiting an invisible point with bizarre, unpredictable shifts in velocity. Further analysis revealed not one, but two distinct gravitational anchors, black holes with masses roughly 12 and 20 times that of our Sun, separated by a mere fraction of a light year. That's close enough in cosmic terms for their mutual pull to distort space-time itself, creating ripples that will eventually spiral outward as gravitational waves. What makes this duo so extraordinary is their endurance. In a cluster packed with hundreds of thousands of stars, close encounters are inevitable. Normally, when two black holes meet, they either merge catastrophically or fling one another into the void like cosmic slingshots. But these two have somehow avoided both fates, settling into a stable orbit that hints at a delicate balance of give and take. One theory suggests they're shielded by a surrounding entourage of stars whose collective gravity acts like a buffer, preventing the black holes from either colliding or being torn apart. Another possibility is that they're relative newcomers, having wandered into each other's grasp only recently after a game of gravitational pinball involving other cluster members. The implications stretch far beyond NGC 3201. If binary black holes are more common in clusters than we thought, they could be prime sources for future gravitational wave detections. Every time these black holes swing close, they lose energy in the form of space-time ripples, inching toward an eventual merger that would shake the universe. Such events might explain some of the mysterious high-energy signals already picked up by observatories like LIGO. But the real mystery lies in what this pair can teach us about cluster dynamics. Their existence suggests that black holes don't just dominate clusters, they might regulate them. As these two dance, their gravitational kicks could be flinging nearby stars outward, shaping the cluster's structure over eons. Some researchers even speculate that binary black holes act as cosmic gatekeepers, controlling how many stars escape the cluster and how many remain trapped in its core. As telescopes continue to monitor this rare duo, one thing is certain: their dance is a slow but relentless one. In 100 million years, they'll spiral closer, their orbits tightening until the final cataclysmic embrace. Until then, they offer a front-row seat to one of the universe's most extreme relationships, a partnership where gravity writes the rules and the stakes are nothing less than the fabric of space itself. Star clusters have always been thought of as celestial cities, crowded neighborhoods where stars live in close quarters, often with planets orbiting them like loyal moons. But what if we told you some clusters might contain more rogue planets, worlds untethered to any star, than actual stars themselves? This mind-bending idea shatters our traditional view of how planetary systems form, suggesting that for every sun in these clusters, there could be dozens, even hundreds, of planets drifting alone in the darkness like cosmic nomads. The evidence comes from places like the Orion Nebula Cluster, a stellar nursery where recent infrared surveys revealed a shocking number of faint, heat-emitting objects too small to be stars yet too massive to be asteroids. These aren't just stray planets ejected from their home systems. They might have formed as rogues, condensing directly from collapsing gas clouds like stars but without enough mass to ignite. Imagine a celestial assembly line where some clouds become stars, others become planets bound to those stars, and a third group, previously overlooked, becomes solitary worlds born free. How could this happen? In the chaotic environment of a young star cluster, gravitational turbulence is constant. Protoplanetary disks, the swirling rings of gas and dust where planets typically form, can be shredded by passing stars or disrupted by intense radiation from nearby giants. Sometimes, chunks of these disks break away, collapsing under their own gravity into rogue planets before they ever orbit a star. Other times, fledgling planets get flung into the void by gravitational slingshots during close encounters with sibling stars. The result, a shadow population of worlds invisible to traditional planet hunting methods, silently outnumbering their star-bound cousins. The implications are staggering. If rogue planets are this common, they could be the universe's dark matter, not in composition, but in sheer unseen abundance. Some estimates suggest there may be 20 times more rogue planets in our galaxy than stars. These lonely worlds could carry frozen oceans beneath their surfaces, preserved by the vacuum of space, or even harbor subsurface life sustained by geothermal heat. And because they don't orbit stars, they'd be nearly impossible to spot unless they pass directly in front of a distant background star, bending its light ever so slightly in a phenomenon called microlensing. But here's the real twist: rogue planets might not stay rogue forever. In dense clusters, a wandering planet could be captured by a passing star, becoming an adoptee in an alien solar system. This could explain bizarre exoplanet discoveries, worlds orbiting backward, or in impossibly tilted paths as survivors of a chaotic past. It also raises a tantalizing question: could our own solar system have stolen a planet or two in its youth? The asteroid belt's odd composition and the hypothetical Planet Nine's distant orbit have led some scientists to wonder if we're already hosting cosmic refugees without knowing it. The more we look, the more these rogue worlds rewrite the rules. They challenge the very definition of a planet. Must it orbit a star, or is it enough to be round and alone? They force us to reconsider where life might persist, untethered from the warmth of a sun. And they hint that the universe's planetary inventory is far richer and far stranger than we ever dreamed. Star clusters, it seems, aren't just homes for stars. They're interstellar orphanages teeming with worlds waiting to be found. Hidden in the constellation Hydra lies a cosmic relic so pristine, it's like stumbling upon an untouched tomb from the dawn of time. The star cluster NGC 4833 doesn't just contain ancient stars, it's a chemical fossil, a preserved snapshot of the universe's raw ingredients before generations of supernova polluted the cosmos with heavier elements. Unlike most clusters where stars show signs of enrichment from stellar explosions, this one's chemistry is eerily pure, nearly devoid of elements like iron, carbon, and oxygen, as if frozen in the first few 100 million years after the Big Bang. Picture opening a vial of air from Earth's earliest atmosphere. That's the level of preservation we're talking about. What makes this cluster so extraordinary is its defiance of cosmic recycling. Most celestial objects are built from recycled material, gas and dust laced with the remnants of dead stars. But NGC 4833 stars formed from primordial hydrogen and helium so uncontaminated, their spectra resemble theoretical models of the universe's first stellar generation. They're the astronomical equivalent of a prehistoric insect trapped in amber, offering a direct line to conditions we've only simulated in supercomputers. Even the cluster's structure is archaic, loosely bound and asymmetrical, unlike the dense globular clusters that dominate our galaxy's halo, suggesting it's a rare survivor from an era before gravity perfected the art of stellar organization. But the real treasure lies in the cluster's lithium content. This lightweight element, forged in the Big Bang, is notoriously fragile, destroyed easily in stellar cores. Yet here, lithium persists in abundances that match predictions of the early universe's composition. It's like finding an unbroken seal on an ancient jar, confirming that no astrophysical process has tampered with the content. This single detail alone helps astronomers calibrate models of cosmic nucleosynthesis, the process that created the universe's first atoms. The implications ripple far beyond astronomy textbooks. If clusters like this were common in the early universe, they might have been the nurseries where the first population Roman 3 stars, hypothetical, massive stars made purely of hydrogen and helium, lived and died. Their supernova would have seeded the cosmos with heavier elements, yet we've never directly observed one. NGC 4833 could be the bridge between that mythical first generation and the metal-rich stars we see today. Yet the mystery deepens when you ask how this cluster stayed so pristine. Most ancient structures were polluted over time by mergers or interstellar winds. One theory suggests it formed in a galactic backwater, a quiet corner where few supernova ever reached. Another posits that it's a captured fragment of a dwarf galaxy so small, it never had the stellar density to trigger extensive chemical recycling. Whatever the reason, its existence forces us to reconsider how efficiently the early universe mixed its materials, and how many other untouched time capsules might still lurk in the cosmic shadows. For astronomers, this cluster isn't just a curiosity, it's a Rosetta Stone. Every photon from its stars carries clues about the universe's chemical infancy, helping us decode how we went from a soup of simple atoms to the complex elements that build planets, life, and even the device you're using right now. And as telescopes grow more sensitive, the hunt for similar fossils intensifies, because each one could rewrite another line in the story of how the cosmos learned to build itself. Among the ancient stellar populations of globular clusters, astronomers have clocked stars spinning at velocities that defy logic, some whirling so fast they're on the verge of tearing themselves apart. These cosmic speed demons, aptly called fast-spinning stars, rotate hundreds of times faster than our Sun, completing full revolutions in mere hours instead of weeks. Picture a figure skater pulling their arms in tight, spinning faster and faster, except these stellar performers are spinning so violently, their equators bulge outward, stretched by centrifugal forces that threaten to fling their outer layers into space. The mystery lies in how these stars reached such extreme speeds. In the dense cores of globular clusters, where stars jostle like commuters in a crowded subway, gravitational encounters are frequent and chaotic. One leading theory suggests these rapid spinners are the products of stellar mergers, cosmic collisions where two stars smash together, combining their angular momentum like a whirlpool fed by two converging rivers. The result is a single, overspun star, its rotation turbocharged by the violent marriage of its predecessors. Another possibility involves binary systems, where one star strips gas from its companion, funneling it onto its surface like water hitting a spinning top, accelerating it to dizzying speeds. But the real enigma comes when we find these fast spinners isolated, far from the cluster's crowded core where collisions should be rare. In the outskirts of Omega Centauri, for example, astronomers discovered a population of these rapid rotators drifting alone, their origins unexplained. This suggests hidden mechanisms might be at play. Perhaps the stars were slingshotted outward after close encounters with black holes, or maybe they're the survivors of long disrupted binary systems, left to spin wildly without a partner to slow them down. The consequences of such extreme rotation are staggering. These stars don't just spin fast, they distort the very fabric of their own existence. Their rapid motion stirs up internal gases, mixing fresh hydrogen into their cores like a blender and extending their lifespans by recycling fuel that would otherwise sit dormant. Some even develop equatorial decretion disks, rings of material flung outward by centrifugal force, creating a celestial hula hoop of glowing gas. And in rare cases, their spin is so extreme, they emit bursts of X-rays or gamma rays, becoming temporary beacons of high-energy radiation in an otherwise quiet cluster. What's truly fascinating is how these stars challenge our models of stellar evolution. Conventional wisdom says old clusters should be filled with sedate, slowly rotating stars, yet here they are, spinning like celestial dervishes billions of years after their formation. Their existence hints that globular clusters aren't the serene retirement homes we once thought, but dynamic arenas where gravity and chance conspire to create stellar oddities. Every fast-spinning star is a cosmic clue, whispering secrets about the violent processes that shape stellar lives in the universe's most crowded neighborhoods. And as telescopes peer deeper, one question lingers. If these stars can defy expectations so dramatically, what other spin-powered surprises are waiting to be uncovered? One of the most perplexing gaps in our cosmic census isn't found in space, it's found in time. When astronomers study star clusters across the universe, they've stumbled upon a bizarre pattern. Countless young clusters blaze with newborn stars, and ancient globulars glow with stellar retirees, but middle-aged clusters seem to be missing almost entirely. It's as if the universe skipped a chapter in its own history, leaving scientists scrambling to explain why star clusters appear to vanish during their cosmic prime. This middle-age gap first became apparent when surveys mapped clusters in galaxies like the Milky Way and Andromeda. The data revealed a striking imbalance. Clusters younger than 100 million years are abundant, and those older than 10 billion years dominate the galactic halo, but clusters between these extremes are strangely rare. Imagine walking into a bustling city and finding only toddlers and elderly citizens with no adults in sight. That's the level of bewilderment this discovery has caused. What could erase entire generations of star clusters? One theory points to galactic violence. Young clusters often form in turbulent spiral arms, where gravitational forces and interstellar winds can rip them apart before they reach middle age. Only the densest, most tightly bound clusters survive these early trials, while the rest dissolve into the galactic backdrop like sandcastles at high tide. Another possibility involves the harsh radiation environments near galactic centers, where extreme UV light from massive stars can evaporate a cluster's gas, scattering its stars before they've aged significantly. But the plot thickens when we look beyond our own galaxy. In the Large Magellanic Cloud, a satellite galaxy rich in star-forming regions, astronomers have found a handful of intermediate-aged clusters proving they can exist. The catch: these survivors are unusually massive, as if only the biggest, toughest clusters endure long enough to reach middle age. This suggests the gap isn't due to a lack of formation, but a brutal filter that eliminates all but the hardiest clusters early on. The implications ripple through our understanding of galactic ecology. If most clusters die young, they may be the primary source of field stars, the isolated suns that populate galaxies without belonging to any cluster. This would mean the glittering backdrop of the Milky Way isn't just made of ancient stars, but the shredded remains of countless failed clusters. Even more intriguing, the middle-age gap might explain why certain types of stars appear rare. If their host clusters dissipated before reaching maturity, those stars would have scattered before we could study them in context. Yet the mystery isn't fully solved. Some simulations suggest the gap could be an observational bias. Middle-aged clusters might simply fade into obscurity, their stars no longer bright enough to stand out against the galactic crowd. Others propose that clusters experience a midlife crisis, undergoing internal upheavals that make them temporarily harder to detect. As telescopes grow more sensitive, the hunt for these missing clusters intensifies, because each one could reveal why some stellar families endure while others fade into cosmic memory. What's certain is that this gap isn't just a quirk, it's a clue. By deciphering why middle-aged clusters seem to disappear, we're uncovering the invisible forces that shape galactic evolution, one star cluster at a time. And as with all cosmic mysteries, the answers might rewrite more than just a single chapter in the story of the universe. Somewhere in the vast cosmic web, a star cluster races through space at speeds so unimaginable. It's essentially a runaway train on an intergalactic track hurtling so fast, it might one day leave its home galaxy behind forever. This isn't science fiction. It's the jaw-dropping reality of hypervelocity star clusters, celestial speedsters defying gravity's grasp with velocities exceeding 1,000 kilometers per second. To put that in perspective, at that speed, you could travel from Earth to the Moon in just under 7 minutes. But what cosmic slingshot could launch an entire cluster, millions of stars bound together, into such a frenzied escape? The leading suspect, a close encounter with a supermassive black hole. Picture a gravitational game of pinball where the cluster swings too close to the monster lurking at its galaxy's center. The black hole's immense pull could fling the cluster outward like a stone from a sling, stealing energy from the cluster's orbit and converting it into raw speed. Another possibility involves the cluster being the survivor of a galactic collision. A cosmic fender bender so violent, it sent the cluster careening through space like a billiard ball knocked off the table. But the real mystery lies in the cluster's survival. Most structures torn apart by such extreme forces would disintegrate, their stars scattered like dust in the wind. Yet hypervelocity clusters hold together, their gravitational bonds resisting the tidal forces that should rip them apart. This suggests they're unusually dense, perhaps packed with dark matter acting as an invisible glue. Or maybe their stars are so tightly knit that not even escape velocity can break their unity. The implications are staggering. If these clusters can break free of their galaxies, they might become intergalactic immigrants, drifting through the void until captured by another galaxy billions of years later. Some could even seed star formation in the barren stretches between galaxies, creating oases of light in the cosmic desert. And if they carry planets' worlds torn from their parent stars during the chaotic escape, those too could become nomads, wandering the darkness with frozen oceans or subterranean life clinging to geothermal heat. Yet the most tantalizing question remains, where are they headed? Simulations suggest some hypervelocity clusters might eventually escape their home supercluster, becoming true orphans of the cosmos. Others could collide with new galaxies, sparking bursts of star formation, or even merging with other clusters in spectacular displays of gravitational choreography. Every hypervelocity cluster is a cosmic detective story, its trajectory a clue to the violent events that shaped its journey. And as telescopes track more of these stellar fugitives, we're left to wonder, are they the exception or just the fastest members of a much larger population of runaway clusters silently racing through the night? One thing's certain, the universe loves a rebel, and these speed demons are rewriting the rules of galactic loyalty one light year at a time. The Phoenix Cluster isn't just another gathering of stars, it's a cosmic rebellion, a stellar uprising in one of the most hostile environments imaginable. Nestled at the heart of a galaxy cluster swimming in superheated gas, this region should be a graveyard for star formation. Temperatures here reach millions of degrees, and the surrounding plasma blasts enough radiation to shred any budding stellar nurseries. Yet against all odds, the Phoenix Cluster is birthing new stars at a rate that dwarfs our own Milky Way, churning out hundreds per year like a relentless cosmic factory. This isn't just a cluster, it's a phoenix rising from the ashes of its own inhospitable universe. What makes this defiance so extraordinary is the physics at play. In most galaxy clusters, the central supermassive black hole acts like a cosmic blowtorch, pumping out jets of energy that heat surrounding gas and suppress star formation. But in the Phoenix Cluster, something's gone haywire. Observations from the Chandra X-ray Observatory reveal a shocking twist. The black hole's outbursts, rather than sterilizing the region, are creating pockets of cooling gas. It's as if a wildfire suddenly started producing rain clouds. These cooling filaments, dense and rich with molecular hydrogen, collapse under their own gravity, igniting furious waves of new stars where none should exist. The real surprise came when astronomers measured the metallicity, the abundance of elements heavier than hydrogen and helium in these newborn stars. They're loaded with metals, far more than expected for stars forming in such a primordial environment. This suggests the cluster isn't just forming stars, it's recycling material on a galactic scale, likely from the remnants of older stellar generations torn apart by tidal forces or supernova. Imagine a cosmic thrift store where the scraps of dead stars become the building blocks for new ones, all within the same furnace. But the Phoenix Cluster's most tantalizing secret might be its timing. It's operating like a relic from the early universe, when star formation ran wild before black holes learned to regulate it. This could mean we're witnessing a rare holdover from that chaotic era, a cluster that never got the memo about slowing down. Alternatively, it might represent a new phase in cluster evolution, one where black holes and star formation reach an uneasy truce. Either way, its existence forces us to reconsider how galaxies grow and change over cosmic time. Every star born in this extreme environment is a challenge to our models, a reminder that the universe still has surprises lurking in its most unforgiving corners. The implications ripple far beyond this one cluster. If stars can form under such brutal conditions, it raises the possibility that other, hostile regions like the neighborhoods around quasars or the wreckage of galaxy collisions might also be hiding stellar nurseries we've overlooked. It even reshapes our search for life. If planets can form in these turbulent cradles, they might orbit stars bathed in radiation, protected only by thick atmospheres or magnetic fields. The Phoenix cluster doesn't just defy expectations, it redefines what's possible, proving that even in the universe's harshest crucibles, creation finds a way. Deep within the ancient stellar cities of globular clusters, astronomers have stumbled upon a baffling cosmic census error, a glaring shortage of red giant stars where theory says there should be crowds. These swollen, aging stars, which should dominate the late stages of a cluster's life, are mysteriously absent in certain clusters, as if someone selectively erased the universe's retirement homes. Imagine attending a reunion where all the elders are missing. That's the unsettling scenario playing out in places like NGC 6712, where red giants are scarcer than predicted by up to 70%. The discrepancy strikes at the heart of stellar evolution models. Red giants form when stars like our Sun exhaust their core hydrogen, puffing up to hundreds of times their original size as they burn helium. Every star cluster with ancient suns should glitter with these luminous behemoths, their numbers meticulously predictable based on the cluster's age and initial composition. Yet when researchers tallied them in certain clusters, the math didn't add up. The leading explanation invokes a brutal process called mass loss, or where stellar winds or binary interactions strip away a star's outer layers prematurely, causing it to skip the red giant phase entirely. Think of it as cosmic forced retirement, where stars shed so much mass they never get the chance to bloat into giants, instead transitioning directly to faint helium-burning dwarfs. But the plot thickens when you examine where these missing giants vanish. In the cluster M4, astronomers found hints that red giants might be hiding in plain sight, their outer atmospheres chemically altered by some unknown process, making them appear cooler and dimmer than expected. It's like someone turned down the thermostat on these stars, camouflaging them among their smaller siblings. Other clusters show evidence of Blue Straggler stars siphoning material from would-be red giants, essentially starving them of the fuel needed to puff up. The most startling twist comes from recent Hubble observations of NGC 6366, where red giants aren't just missing, they're being ejected. The cluster's dense core acts like a gravitational slingshot, flinging these bulky stars outward before they can complete their life cycle. High-resolution imaging reveals trails of displaced red giants drifting in the cluster's outskirts, exiled by gravitational encounters with binary stars or black holes. This could mean we've been looking in the wrong places, and the missing giants are actually refugees, banished to the cosmic suburbs. The implications rewrite our understanding of stellar demographics. If red giants can be erased from the visible record through ejection or premature transformation, astronomers may need to recalibrate how they estimate cluster ages and compositions. Entire chapters of stellar evolution textbooks might require edits to account for these hidden retirement paths. Even more intriguing, the missing giants problem might hold clues to the fate of our own Sun. If external factors like a close orbiting companion star or turbulent cluster environment can alter a star's aging process, then the classic red giant to white dwarf sequence isn't universal. Some stars, it seems, take the cosmic backdoor to old age, leaving us to piece together their secrets from the gaps they leave behind. As telescopes probe deeper into these enigmatic clusters, one thing becomes clear: the universe loves a good Magritte painting. Sometimes what's most revealing isn't what we see, but what we expected to see and didn't. The missing red giants aren't just an astronomical accounting error. They're a doorway into the chaotic, unseen forces that shape how stars live, age, and ultimately fade from view. Buried in the depths of the constellation Fornax lies a cosmic illusion, a star cluster that appears nearly empty through most telescopes, its true nature hidden in the shadows. This is the so-called dark star cluster, where 99% of the stellar population consists of dim, low-mass red dwarfs and failed stars called brown dwarfs, objects so faint they emit barely a whisper of visible light. What looks like a sparse collection of a few dozen stars is actually a teeming metropolis of hundreds, perhaps thousands, of stellar underdogs, invisible to all but the most sensitive infrared eyes. Traditional star surveys missed this ghostly gathering entirely because they relied on optical light, the same wavelengths our eyes perceive. But when astronomers pointed infrared telescopes like the James Webb Space Telescope toward this region, the truth emerged: a swarm of ultra-cool dwarfs, each no larger than Jupiter and some barely hot enough to sustain fusion in their cores. These stars are the universe's wallflowers, emitting most of their energy in the infrared spectrum, their surfaces so cool you could theoretically touch them without being vaporized. The implications rewrite our understanding of cluster demographics. If this dark cluster isn't unique, there could be entire populations of similar structures lurking undetected throughout the galaxy, masquerading as empty patches of sky. Some estimates suggest these shadowy clusters might outnumber their brighter counterparts, hidden in plain sight because our tools were tuned to the wrong frequency. What's truly bizarre is how this cluster defies the usual rules of star formation. Most stellar nurseries produce a range of stars, a few massive blue giants, many sun-like stars, and a scattering of small red dwarfs. But here, the distribution is wildly skewed, as if some cosmic filter prevented anything larger than a fraction of our sun's mass from forming. One theory suggests the cluster was born in an unusually sparse molecular cloud, where turbulence and magnetic fields suppressed the formation of heavier stars. Another proposes it's the remnant of a larger cluster, stripped of its brighter members by gravitational interactions, leaving only the faintest behind like survivors of an unseen catastrophe. Then there's the brown dwarf enigma. These failed stars, too small to ignite hydrogen fusion, glow dimly from the heat of their formation. In most clusters they're rare, but here they might outnumber the red dwarfs. Some even show evidence of swirling storm systems, like Jupiter's great red spot scaled up to stellar proportions. If clusters like this are common, the galaxy's census of brown dwarfs and their potential to host rogue planets might need a drastic upward revision. The discovery forces a humbling realization. We've been mapping the cosmos with a blindfold, seeing only the brightest players while missing the quiet majority. Every faint flicker in this dark cluster whispers a question: how many more are out there, and what secrets do they hold about the universe's hidden stellar underclass? As infrared astronomy advances, one thing becomes clear: the night sky is far more crowded than we ever imagined. In the vast expanse of the Milky Way, astronomers have found a celestial puzzle that defies coincidence. Two star clusters separated by thousands of light years, yet mirroring each other with uncanny precision. Known as the twin clusters, these stellar siblings share nearly identical sizes, shapes, chemical compositions, and even star counts, as if the universe hit copy-paste across the galaxy. The odds of such a match occurring by chance are staggeringly low, raising a tantalizing question. Could these clusters be long-lost relatives torn apart by some ancient cosmic upheaval? The first twin, NGC 2157, glitters in the constellation Dorado, while its counterpart, NGC 3136, resides far away in Antlia. At first glance, they appear as ordinary open clusters, loose gatherings of young, blue-white stars. But when astronomers analyzed their light spectra, the similarities became undeniable. Both clusters contain stars with matching ratios of iron, oxygen, and rare elements like europium, a chemical fingerprint so specific, it's like finding two distant families with identical DNA. Even their ages align within a few million years, suggesting they formed around the same cosmic epoch under eerily similar conditions. The leading theory involves a galactic collision. Billions of years ago, the Milky Way may have cannibalized a smaller satellite galaxy, ripping apart its star-forming clouds in the process. If one of those clouds fragmented into two massive clumps before spawning stars, the resulting clusters would inherit near-identical properties like twins separated at birth. Supporting this idea, both clusters orbit the galaxy on similar, highly inclined paths, a telltale sign of an extragalactic origin. But the mystery deepens when you examine their current environments. NGC 2157 sits in a relatively quiet region, while NGC 3136 drifts near a turbulent spiral arm. Despite these differences, both have maintained their structural integrity, resisting the gravitational tides that typically distort clusters over time. This resilience hints at an unseen factor, perhaps an unusually high concentration of dark matter binding them together, or an original density so extreme that even galactic forces struggle to tear them apart. The implications stretch far beyond these two clusters. If twins can form and survive such separation, the Milky Way might be dotted with other stellar siblings we've yet to pair up. Some researchers speculate that famous clusters like the Pleiades or Hyades could have long-lost matches lurking in uncharted regions of the galaxy. Others wonder if the twin phenomenon extends to globular clusters, with ancient counterparts waiting to be discovered in the galactic halo. What's truly remarkable is how these twins challenge our assumptions about stellar birth. We've long assumed that star clusters form in isolation, shaped by local conditions. But if clusters can emerge as matched sets, it suggests that the universe occasionally operates on an assembly line, stamping out celestial objects with factory-like consistency. Every glance at these twins is a reminder that the cosmos still holds patterns we've only begun to trace, and that sometimes the most profound connections are written in starlight, waiting for us to piece them together. Deep in the constellation Perseus, astronomers have uncovered a star cluster that shouldn't glow the way it does, at least, not according to everything we know about stellar physics. Officially catalogued as NGC 1261, this cluster earned the nickname X-ray mystery for one baffling reason. It's emitting X-rays at an intensity that dwarfs all predictions, as if someone left a cosmic stove burning at full blast. The strangest part, there's no visible source, no active black hole, no neutron star collisions, no supernova remnants, just a diffuse, pervasive glow of high-energy radiation that defies explanation. At first glance, NGC 1261 appears ordinary, a dense grouping of ancient stars bound by gravity like countless others. But when the Chandra X-ray Observatory trained its gaze on the cluster, the data revealed something extraordinary. The X-rays weren't concentrated at the core, where massive objects like black holes typically lurk, but spread evenly throughout the cluster like a fog. This uniform emission suggests a collective phenomenon, something woven into the fabric of the cluster itself. One leading theory points to a hidden population of stellar corpses, white dwarfs and neutron stars too faint to spot individually, but collectively pumping out X-rays as they siphon gas from companion stars or collide with interstellar material. Yet even that explanation falls short. Simulations show the combined output of these objects couldn't account for the sheer volume of X-rays observed. That's where darker possibilities emerge. Some researchers speculate the cluster might be saturated with dark matter particles that annihilate upon contact, releasing bursts of energy as they vanish. If true, NGC 1261 could be a rare window into dark matter's behavior, with the X-rays acting as a tracer for interactions we've never directly detected. Others propose the cluster harbors dozens of intermediate mass black holes, objects too small to dominate the core, but numerous enough to heat the entire environment through their combined activity. The plot thickens when you examine the cluster's history. Unlike most globular clusters which orbit placidly in galactic halos, NGC 1261 shows signs of a violent past. Its stars move in chaotic, unpredictable patterns, hinting at a close encounter with another massive object, perhaps a galaxy or another cluster, that stirred its depths like a spoon in a cup of coffee. Could that turbulence have triggered a cascade of stellar collisions or awakened dormant black holes, leaving behind this X-ray afterglow? Or is the cluster's abnormal chemistry to blame? Spectroscopy reveals unusually high concentrations of heavy elements, suggesting its stars might be polluted by the remnants of ancient supernova, whose decaying radioactive isotopes could still be emitting X-rays billions of years later. The implications stretch far beyond this one enigma. If the X-rays stem from dark matter, it could redefine how we search for this elusive substance. If they're the work of hidden black holes, it suggests clusters might be far more dynamic and dangerous than we imagined. Even if the answer lies in some mundane stellar process we've overlooked, the very existence of this mystery reminds us how much we still don't understand about the universe's most crowded neighborhoods. NGC 1261 isn't just a cluster. It's a cosmic detective story, and every flicker of its unexplained X-rays is a clue waiting to be deciphered. Globular clusters are supposed to be cosmic retirement homes, ancient gatherings of stars that formed in the universe's chaotic infancy and have aged together for billions of years. So when astronomers pointed telescopes at a cluster called NGC 2173 in the constellation Orion, they expected to see the usual crowd of elderly stars. Instead, they found something that shouldn't exist, a globular cluster sparkling with stellar teenagers, their brilliant blue-white light cutting through the expected sea of golden oldies like fireworks in a quiet library. This discovery flips everything we thought we knew about how globular clusters form and evolve. These clusters are typically fossils from the early universe, where all stars were born in a single, frenzied burst of star formation within the first few billion years after the Big Bang. They shouldn't host young stars, yet NGC 2173 does, with some as youthful as 100 million years old. That's like finding a kindergarten classroom inside a medieval castle. How did these stellar youngsters end up in a place meant for the ancients? One theory suggests the cluster might have cannibalized a passing gas cloud, igniting a late-in-life baby boom. Imagine an elderly neighborhood suddenly building new houses because a construction truck accidentally dumped supplies in their park. Another possibility is even wilder. The cluster could be harboring a secret stash of stellar rejuvenators, blue straggler stars formed from collisions or stolen fuel that look deceptively young despite their true age. But the most tantalizing explanation involves dark matter. Some simulations show that if a globular cluster is embedded in a dense halo of dark matter, the gravitational interactions could trigger sporadic star formation even billions of years after its birth. This would mean NGC 2173 isn't just a cluster, it's a cosmic time machine where the invisible hand of dark matter keeps rewriting the rules of stellar life cycles. The implications are revolutionary. If young stars can form in globular clusters, it challenges the clean division between open clusters, young, loose stellar families, and globulars, ancient, dense relics. It also raises questions about how many other globulars might hide similar surprises. Telescopes are now scouring other clusters for signs of youthful outliers, and every discovery, or lack thereof, forces us to rethink our models of how the universe builds and rebuilds its stellar cities. NGC 2173 stands as a living contradiction, proving that even the oldest corners of the cosmos still have a few tricks up their sleeves. Whether it's through theft, collisions, or dark magic, this cluster refuses to fade quietly into the night. And in doing so, it reminds us that the universe's history is still being written, one rebellious star at a time. In the constellation of Hercules, two ancient star clusters are locked in a cosmic ballet so slow, human civilizations could rise and fall before we'd notice their motion. NGC 6266 and NGC 6267 appear serene through telescopes separated by a mere 40 light-years, but this tranquility is an illusion. These clusters are actually mid-collision, their stars gradually intertwining in a gravitational waltz that offers us a rare preview of how stellar cities merge over cosmic timescales. Imagine two soap bubbles drifting toward each other, gently deforming as they touch, their surfaces rippling but never popping. That's the delicate dance unfolding here, played out over millions of years. What makes this interaction extraordinary isn't just its rarity, it's the forensic evidence it leaves behind. As the clusters spiral closer, their mutual gravity stretches streams of stars into luminous bridges between them, like taffy pulled between two hands. These tidal tales, though beautiful, reveal the violence beneath the surface. Stars torn from their original orbits, hurled into chaotic new trajectories. Yet despite this chaos, neither cluster has lost its identity. Their cores remain densely packed, resisting disruption like two dancers maintaining their footing while their scarves flutter wildly around them. This resilience challenges assumptions that globular clusters should dissolve easily during mergers, suggesting their gravitational bonds run deeper than we thought. The real goldmine for astronomers lies in the collision's side effects. As stars from each cluster mingle, their unique chemical fingerprints, vestiges of their birth clouds, begin to blend. NGC 6267 stars show higher traces of heavy elements like iron, hinting it formed in a more polluted region of space than its partner. By mapping how these metallicities mix, researchers can trace which stars originated where, effectively reconstructing the cluster's pre-collision histories. It's like analyzing the ingredients in two batches of dough as they're kneaded together, discerning which flour came from which sack. But the most startling revelation came from Hubble observations of Blue Stragglers, rejuvenated stars born from collisions or stolen fuel. These outliers cluster along the bridge between NGC 6266 and NGC 6267, glowing brighter and bluer than their peers. Their positioning suggests the merger is sparking stellar second acts, as close encounters between stars from opposite clusters trigger new rounds of star formation. Think of it as a celestial renaissance where the chaos of collision births fresh creativity. This slow-motion merger also serves as a preview of our Milky Way's future. When our galaxy collides with Andromeda in 4 billion years, such interactions will play out on a grander scale, with star clusters from both galaxies weaving similar gravitational tapestries. By studying these Herculean clusters now, we're glimpsing the opening notes of a symphony that will define the next epoch of cosmic history, one where even the oldest stellar gatherings aren't immune to change, and where destruction and rebirth are two sides of the same celestial coin. Scattered across the Milky Way like cosmic orphans, millions of stars drift alone, no cluster to call home, no stellar siblings to orbit alongside. These solitary wanderers pose a celestial riddle. If stars are born in crowded nurseries, how did these suns end up exiled into the galactic wilderness? The answer lies in the violent dynamics of star clusters, where gravitational encounters can fling stars outward with enough force to escape forever, turning them into permanent drifters in the vast ocean of space. Consider the case of HD 162806, a rogue star hurtling through the Milky Way at nearly 700,000 miles per hour, fast enough to cross the distance from Earth to the Moon in under 30 minutes. Spectroscopy reveals its composition matches the stars of the globular cluster Omega Centauri, a smoking gun proving it was violently ejected, the culprit. A close encounter with the cluster's intermediate mass black hole, which acted like a gravitational slingshot, accelerating the star to escape velocity. Other runaway stars show similar chemical fingerprints linking them to clusters, their trajectories tracing back to ancient explosive events we can only reconstruct through forensic astronomy. But ejection isn't always a one-star affair. Some clusters experience tidal stripping, where galactic forces peel away stars like layers of an onion. The Arcturus stream, a river of stars arcing across the northern sky, is believed to be the shredded remains of a dwarf galaxy or globular cluster torn apart by the Milky Way's gravity over billions of years. Here, the stars weren't ejected individually but discarded en masse, like a cosmic tornado scattering debris across the countryside. Unlike hypervelocity stars shot from black holes, these tidal orphans retain slower, more meandering paths, their collective motion betraying their shared origins. The most haunting orphans might be those never truly born into a cluster. Recent surveys have uncovered isolated young stars in galactic voids far from any known stellar nursery. One theory suggests they formed in dark molecular clouds too faint to detect, collapsing in isolation like cosmic hermits. Another proposes they were born in clusters so sparse they dissolved almost immediately, leaving no trace beyond these wandering progeny. These stars challenge the very definition of orphanhood. Were they abandoned, or did they emerge into solitude from the start? Astronomers now suspect these lone stars play a hidden role in galactic ecology. As they wander, they may seed planets with heavy elements from their stellar winds or even deliver frozen organic molecules to new systems. Some could host rogue planets of their own, ejected during the same chaotic events that liberated their parent stars. And in rare cases, two orphaned stars might collide in the darkness, igniting temporary beacons visible across the galaxy, a fleeting reunion in the void. Their existence reshapes how we map the Milky Way's history. Like breadcrumbs left by a passing giant, these stars mark where clusters once roamed and dissolved, their trajectories encoding ancient gravitational upheavals. Every solitary sun is a clue, a silent witness to the universe's relentless reordering, proof that even in space, no family bond is truly unbreakable. And as telescopes grow sharper, we're left to wonder how many more orphans drift unseen, their stories written in light we've yet to collect. Tucked away in the dim outskirts of the Milky Way, a ghostly smudge of starlight barely registers against the cosmic backdrop. This is the ultra-faint cluster Segway 1, a celestial relic so ancient and sparse it verges on invisibility. Unlike the glittering metropolises of globular clusters, Segway 1 contains just a few hundred stars scattered across 30 light-years, their combined light output weaker than a single red giant star. Yet this faint whisper of a cluster holds secrets that punch far above its weight. It may be a survivor from the universe's first wave of star formation, a living fossil from an era when galaxies were nothing more than hazy ideas. What makes Segway 1 extraordinary isn't just its age, estimated at over 13 billion years, but its chemical purity. The stars here are virtually metal-free, composed almost entirely of hydrogen and helium, the raw materials forged in the Big Bang. This pristine composition suggests they formed before supernova had a chance to seed the cosmos with heavier elements, making them potential descendants of the legendary population Roman 3 stars, the universe's first luminous object. Finding Segway 1 is like stumbling upon a cave painting untouched by time, its simplicity telling a story older than the Milky Way itself. Detecting such a feeble cluster required ingenious methods. Traditional surveys missed it entirely because its stars are so dim and widely spaced. Astronomers only spotted it by tracking subtle stellar motions, the way its stars drift in unison like a school of fish in a dark ocean. Even then, its true nature wasn't clear until spectroscopic analysis revealed the star's primordial chemistry. The cluster's velocity and orbit added another clue. It's not circling the Milky Way like modern clusters, but plunging through it on a chaotic path, a hallmark of an object captured rather than born here. The implications of this discovery ripple through cosmology. If Segway 1 is indeed a first-generation cluster, its stars could help calibrate models of the early universe's conditions. Their lack of metals supports theories that the first stars were monstrously massive, burning bright and fast before exploding in supernova so violent they scattered the first heavy elements into the void. Yet Segway 1's mere existence poses a puzzle. How did such a fragile structure survive the cosmic turbulence of 13 billion years? Most clusters this small should have been shredded by galactic tides long ago. One radical explanation involves dark matter. Simulations suggest Segway 1 might be embedded in a dense, invisible halo that acts like a gravitational shield, preserving it against disruption. If true, this would make it not just a stellar cluster but the stripped core of a dwarf galaxy. It stars the last visible remnants of a much larger system devoured by the Milky Way. That would mean we're looking at a galactic ghost, its true mass hidden in the dark. The hunt for similar ultra-faint clusters has since exploded, with telescopes like Gaia and James Webb scanning the skies for these cosmic whispers. Each new discovery chips away at our understanding of how structure emerged in the infant universe. Segway 1 stars, though faint, shine a light on our deepest origins, proof that sometimes the quietest voices tell the loudest stories. And as astronomers decode their subtle language, one thing becomes clear. The universe's earliest chapters are still being read, written in starlight that barely glows. Most star clusters sprinkle supernova across the cosmos like rare fireworks, maybe one every few centuries if they're lucky. But in the depths of the small Magellanic Cloud, astronomers found a cluster that laughs in the face of cosmic moderation. NGC 3466, a stellar assembly line churning out supernova like a conveyor belt of doom. This isn't just a cluster with occasional stellar explosions, it's a full-blown supernova factory where massive stars live fast, die young, and leave behind a glittering graveyard of neutron stars and black holes at a rate 10 times higher than anywhere else in the local universe. What makes this cluster so explosively productive starts with its staggering density. Packed into a region just 40 light-years across are hundreds of scorching hot O-type stars, celestial titans, each weighing over 20 times our Sun's mass. These aren't just any massive stars, they're stellar siblings born from the same dense, chemically enriched gas cloud, meaning they share a terrifyingly short expiration date. While typical star clusters might host one or two such monsters, NGC 3466 has dozens, setting the stage for a chain reaction of destruction. The carnage unfolds in waves. Every few decades, another one of these behemoths exhausts its nuclear fuel and collapses in a type Roman II supernova, its core imploding while its outer layers blast outward at 20,000 miles per second. Shock waves from these explosions ripple through the cluster, compressing nearby gas clouds and triggering fresh rounds of star formation, including the next generation of supernova progenitors. It's a self-sustaining cycle of death and rebirth, where each stellar detonation plants the seeds for future explosions. But here's the twist that stunned researchers. This cluster's supernova aren't just frequent, they're weirdly uniform. Spectroscopic analysis reveals nearly identical light curves and elemental signatures in each explosion, suggesting the stars are dying in eerily similar ways. This could mean they formed with nearly identical compositions, like bullets loaded into the same cosmic gun. The resulting heavy elements oxygen, silicon, iron don't drift away as usual but linger in the cluster's gravitational grip, enriching subsequent stellar generations in a feedback loop that's rewriting our understanding of chemical evolution. The implications stretch far beyond this one cluster. If supernova factories like this were common in the early universe, they could explain mysterious pockets of ultra-enriched gas in distant galaxies. Some theorists even suggest NGC 3466 might resemble the starburst clusters that built the first heavy elements after the Big Bang, acting as cosmic crucibles where the raw materials for planets and life were forged in relentless stellar infernos. Yet the most unsettling question remains unanswered. What happens when all these ticking time bombs go off? Simulations show the combined energy of future supernova could eventually blow the cluster apart, scattering its remnants across intergalactic space like shrapnel from a grenade. Until then, this celestial demolition derby offers a front-row seat to the universe's most violent recycling program, where death isn't an end but fuel for the next cosmic construction project. Bursting through the cosmic void at over 3 million miles per hour, a rogue black hole carves a path of chaos, an invisible fugitive fleeing the scene of an ancient gravitational crime. This isn't just any wandering singularity. It's a runaway supermassive black hole, violently ejected from its home cluster in a collision so cataclysmic, it left a trail of star formation glowing in its wake like cosmic breadcrumbs. The discovery rewrites our understanding of how black holes interact, proving these gravitational monsters don't just lurk at galactic centers, they can be hurled into intergalactic space like celestial billiard balls. The drama began when astronomers spotted an anomalous streak of young, blue stars stretching across 30,000 light-years, a structure too linear and too turbulent to form naturally. At its tip, an invisible gravitational anchor bending the light of background galaxies in telltale warps. Follow-up X-ray observations revealed the truth. A supermassive black hole weighing as much as 20 million suns, racing through intergalactic space so fast it would cross from Earth to Neptune in just 14 minutes. The starburst tail isn't just collateral damage, it's the shock wave of the black hole's escape, compressing interstellar gas into stellar nurseries as it plows through the cosmos. How does a black hole, an object so gravitationally dominant, get kicked out of its home? The answer lies in a cosmic three-body problem. When two galaxies merge, their central black holes spiral toward each other, eventually colliding in a gravitational wave crescendo. If a third black hole enters the dance, the complex interplay can slingshot one of them outward at unimaginable speeds. Simulations show these ejections happen more often than we thought, with the escaping black hole carrying enough momentum to break free of its host cluster entirely. The aftermath tells a forensic story. The runaway's trail isn't uniform, it flickers with gaps where star formation stutters, revealing periods when the black hole plunged through denser gas clouds or veered closer to galactic disks. Some sections even show evidence of twisted magnetic fields, suggesting the black hole's passage whipped the interstellar medium into violent turbulence. And the home cluster left behind, it bears the scars of imbalanced stars orbiting erratically, as if still reeling from the gravitational shock of losing its central anchor. What's truly staggering is the scale of this exile. Most ejected objects we found, like hypervelocity stars, are small fry compared to a supermassive black hole. This one's escape required energy equivalent to 100 simultaneous supernova, a testament to the universe's capacity for violence. If such events are common, the cosmic web might be threaded with invisible rogue black holes, drifting unseen until they disturb some unlucky galaxy's outskirts. The discovery forces us to reconsider how structures grow. If black holes can be evicted, then galaxy formation isn't just about accumulation, it's also about loss. Some clusters might be missing their central engines entirely, their stars orbiting an empty throne. Others could host multiple black holes in unstable dances, each ejection leaving behind a new king until the next merger unsettles the balance. And for planets orbiting stars in these systems, the sudden departure of their cluster's gravitational heart could send them spiraling into darkness or flinging them toward new orbits in a celestial reshuffling. As telescopes trace more of these high-speed outcasts, one thing becomes clear: the universe plays for keeps. Even the mightiest objects aren't immune to exile, and the trails they leave behind, whether glowing ribbons of new stars or twisted magnetic wakes, are graffiti tags on the cosmos proclaiming, "Gravity always wins, and its battles leave marks that last for eons." In the cosmic hierarchy of black holes, there's a glaring gap that keeps astronomers up at night: the elusive intermediate mass black holes. Theory predicts these mid-sized titans, with masses between 100 and 100,000 times that of our Sun, should lurk in star clusters as stepping stones between stellar mass black holes and supermassive behemoths. Yet despite decades of searching, these celestial Goldilocks, neither too small nor too large, remain frustratingly absent from places they should dominate. Take the case of Omega Centauri, the Milky Way's largest globular cluster. Packed with millions of stars, its core should host an intermediate mass black hole weighing at least 10,000 suns. Yet repeated observations show nothing but chaotic stellar orbits, moving as if tugged by multiple smaller black holes rather than a single central anchor. It's like shaking a box full of marbles and hearing the rattle of many small objects instead of the thud of one heavy weight. Similar voids appear in other massive clusters like M15 and G1, where gravitational models insist a middleweight black hole should exist, but the only evidence is its conspicuous absence. The mystery deepens when we consider how these objects should form. Intermediate mass black holes are thought to grow either from the collapse of primordial gas clouds in the early universe or through runaway mergers in dense star clusters. In the latter scenario, smaller black holes would sink to a cluster's core through dynamical friction, collide, and merge over eons into ever larger objects. Yet something seems to be interrupting this process. Perhaps gravitational kicks during mergers that eject the growing black hole before it reaches intermediate mass. Alternative explanations only add to the puzzle. Some researchers suggest these black holes might be hiding in plain sight, masquerading as tight groups of stellar mass black holes whose combined gravity mimics a single larger object. Others propose they're cloaked by thick accretion disks that absorb their telltale X-ray emissions. The most radical theory, that intermediate mass black holes form differently than we think, perhaps through exotic dark matter interactions or quantum processes in the early universe that left them scattered in unexpected places. The implications ripple across astrophysics. If these black holes truly are missing from clusters, it could mean our understanding of gravitational dynamics is incomplete. Their absence might explain why some clusters appear puffier than models predict without a central anchor. Stars would orbit more chaotically. It also throws a wrench into theories of how supermassive black holes grow, since intermediate mass versions were thought to be their building blocks. Yet hope isn't lost. New detection methods like tracking the subtle wobbles of stars or hunting for gravitational waves from elusive mergers may soon unveil these cosmic phantoms. Until then, their absence remains one of astronomy's most nagging open cases, a reminder that even our best theories still have gaps waiting to be filled by the universe's next great discovery. Among the countless star clusters lighting up the observable universe, astronomers have stumbled upon measurements so perplexing they threaten to upend our fundamental understanding of cosmic expansion. The discrepancy centers on dark energy, the mysterious force accelerating the universe's growth, and how its effects appear wildly inconsistent when observed in different cluster environments. While textbooks describe dark energy as a uniform pressure stretching space-time, certain clusters show gravitational distortions suggesting localized variations in this enigmatic force, as if the universe's expansion engine sputters unpredictably in crowded stellar neighborhoods. Take the case of the Coma Cluster, a massive gathering of galaxies roughly 320 million light-years away. When researchers measured the velocities of its member galaxies, they expected to see motion consistent with dark energy's predicted influence, a steady outward acceleration. Instead, they found peculiar pockets where galaxies moved as if dark energy's push were weaker, or in some regions, bizarrely absent altogether. It's like blowing up a balloon only to find certain patches refusing to stretch, defying the uniform expansion you'd expect. These anomalies can't be explained by visible mass alone, leaving scientists scrambling to reconcile them with the standard cosmological model. One radical theory suggests dark energy might interact differently in extreme gravitational environments. In most of the universe, it operates unimpeded, smoothly accelerating expansion in the near-perfect vacuum of intergalactic space. But within dense clusters where gravity warps space-time into deep wells, dark energy could become screened, its effects dampened or modified by the competing pull of matter. This idea, loosely termed chameleon theory, proposes dark energy's strength varies depending on its surroundings, much like a chameleon changing color to match its environment. If true, it would mean Einstein's cosmological constant isn't so constant after all, but a dynamic force that flexes with local conditions. Yet another puzzling piece of evidence comes from the Hubble constant tension, the growing disparity in measurements of the universe's expansion rate. Clusters like Virgo and Fornax show expansion velocities up to 7% slower than predictions derived from the cosmic microwave background. Some researchers argue this mismatch could hint at dark energy growing stronger over time, or perhaps clustering unevenly across the cosmos like an invisible cosmic foam. Others propose these anomalies stem from undiscovered particle interactions or even flaws in how we calibrate cosmic distances. The implications ripple far beyond academic curiosity. If dark energy's behavior is context-dependent, it could reshape our predictions for the universe's ultimate fate. Current models forecast a big freeze, where relentless expansion isolates galaxies in cold, empty darkness. But if dark energy weakens in high-density regions, clusters might remain gravitationally bound longer than expected, preserving islands of structure in an otherwise dissipating cosmos. Alternatively, should these anomalies signal an even stranger physics like dark energy merging with dark matter in dense environments, we might need a complete overhaul of how we define fundamental forces. For now, the anomalies remain unresolved, a quiet challenge to cosmology's status quo. Every contradictory data point is a breadcrumb leading toward a deeper truth, reminding us that the universe's greatest mysteries often hide in plain sight, woven into the very fabric of the cosmic structures we thought we understood. As telescopes gather more precise cluster measurements, one thing becomes clear. Dark energy's story is far from finished, and its next chapter could rewrite the rules of reality itself. Floating silently in the cosmic darkness, some star clusters radiate an eerie glow that shouldn't exist, a persistent hum of gamma rays with no obvious source. These high-energy emissions envelop entire clusters like ghostly halos, puzzling astronomers who have traced the gamma rays back to nothing. No pulsars, no black holes, no supernova remnants, just empty space thrumming with invisible energy. The leading suspect, dark matter, the universe's most elusive substance, may be disintegrating at the edges of these clusters, leaving behind gamma-ray fingerprints of its long-awaited decay. The smoking gun emerged when telescopes like Fermi LAT scanned clusters such as Fornax and Coma, detecting gamma-ray signals precisely matching theoretical predictions for dark matter annihilation. According to leading models, when two weakly interacting massive particles, hypothetical dark matter building blocks, collide, they could annihilate in a flash of gamma radiation. The eerie part, the signals peak at energy levels around 1 to 3 gigaelectronvolts, a sweet spot that aligns perfectly with what many physicists expect from certain dark matter particle decays. It's like finding a murder weapon at a crime scene that fits only one suspect's hands, yet the mystery deepens when you examine alternative explanations. Some researchers argue these gamma rays could come from an unseen population of millisecond pulsars, rapidly spinning neutron stars too faint to detect individually but collectively powerful. Others point to cosmic rays interacting with cluster gas as a potential source, But here's the catch: the gamma-ray distribution doesn't match these scenarios. The emissions aren't concentrated in the cluster cores where pulsars would gather, nor do they correlate with visible gas clouds. Instead, they form smooth, spherical halos, exactly what you'd expect if dark matter particles were decaying uniformly throughout the cluster's invisible gravitational field. The implications could rewrite particle physics. If confirmed, these gamma-ray halos would provide the first direct evidence that dark matter isn't just gravitational scaffolding. It's a dynamic substance capable of interactions beyond gravity. Certain theories, like supersymmetry, predict such particles would annihilate into standard model particles, including gamma rays under specific conditions. The detected energy signatures even hint at possible particle masses around 30 to 60 times that of a proton, placing dark matter squarely in the WIMP, weakly interacting massive particle category, long favored by theorists. But the plot thickens when we compare clusters. Some, like Virgo, show strong gamma-ray excesses, while others of similar size and mass reveal nothing. This inconsistency might trace back to differing dark matter densities or cluster collision histories. Violent mergers could have compressed dark matter concentrations, boosting annihilation rates. Or perhaps the variations point to multiple dark matter particle types, each with unique decay signatures. The uncertainty has sparked a new era of multi-messenger astronomy, where teams combine gamma-ray data with gravitational lensing maps and neutrino detectors to triangulate the truth. What makes this hunt so thrilling is the stakes. Dark matter constitutes 85% of the universe's mass, yet we've only inferred its presence through gravitational effects. Catching it in the act of decay would be like finally seeing the invisible elephant in the room, not just by the footprints it leaves, but by hearing its trumpet. Every unexplained gamma-ray photon from these clusters carries a potential message from the dark sector, and as detectors grow more sensitive, we're not just searching for answers anymore. We're listening to the universe whisper its deepest secrets in a language of light we're only beginning to decode. In the crowded stellar neighborhoods of star clusters, some stars don't just age gracefully, they cheat. These celestial con artists, known as stellar vampires, lurk in binary systems where one star drains the lifeblood of its companion, siphoning away gas and dramatically altering the fates of both. Picture a cosmic parasite, its gravitational tendrils latched onto a neighbor, pulling material across the gap between them like a celestial straw. These aren't just oddities, they're stellar time machines where theft rewrites the rules of stellar evolution. The process begins with proximity. In clusters where stars are packed tight, binary systems often form with one star more massive than the other. Over time, the more massive star burns through its fuel faster, swelling into a red giant. But if its companion lingers too close, the giant's outer layers, loosely bound by gravity, can spill across the gap, pulled by the smaller star's hunger. This stolen gas spirals inward, forming a luminous accretion disk that glows with X-rays as it funnels onto the thief's surface. The donor star, now stripped of its outer hydrogen, collapses into a helium-burning husk, while the vampiric star bulks up, rejuvenated by its ill-gotten fuel. What makes these systems truly bizarre is how they defy expectations. Take the case of the Blue Stragglers stars that appear inexplicably young and bright in ancient clusters. These anomalies were once a mystery until astronomers realized they're the products of stellar theft. By cannibalizing their partners, these stars reset their internal clocks, mixing fresh hydrogen into their cores and extending their lifespans by billions of years. It's as if a senior citizen robbed a blood bank and emerged looking like a teenager. But the cosmic robbery doesn't always go smoothly. In some systems, like the infamous Black Widow pulsars, the thief takes things too far. These ultra-dense neutron stars blast their donors with deadly radiation and particle winds, slowly evaporating them into nothingness. The donor star's material, instead of settling gently onto the pulsar, gets superheated into plasma, creating shock waves that glow across the electromagnetic spectrum. Over millennia, the victim star shrinks to a cinder, leaving the vampiric pulsar alone until it sets its sights on a new target. The aftermath of these feeding frenzies can be just as strange. Some donor stars, stripped down to their helium cores, become subdwarfs, hot, compact stars that burn furiously but briefly before fading away. Others, if enough mass is stolen, might skip the red giant phase entirely, transitioning directly into white dwarfs without the usual fanfare. Meanwhile, the vampire star, now bloated with stolen fuel, might explode as a supernova far sooner than it would have naturally, its life cut short by its own gluttony. These systems aren't just macabre curiosities, they're cosmic laboratories. By studying them, astronomers can test theories of stellar evolution under extreme conditions, watching how stars behave when their lifespans are hijacked by gravitational robbery. They also hint at a darker truth about star clusters. Survival isn't just about size or brightness, but about who's willing to steal and who's left to wither. Every vampiric binary is a reminder that even in the vastness of space, the universe has a taste for drama, where the line between predator and prey is written in starlight and fire. In the cosmic arena of star clusters, one heavyweight contender stands out not for its size alone, but for its ruthless appetite. The so-called cannibal cluster, officially known as NGC 7622, isn't just growing passively through mergers. It's actively devouring smaller neighbors in a gravitational feeding frenzy that reshapes our understanding of how these structures evolve. Imagine a galactic-scale predator, its gravity acting like cosmic claws, tearing apart weaker clusters and absorbing their stars into its own sprawling bulk. This isn't just survival of the fittest, it's celestial gluttony on a staggering scale. The evidence of this cluster's voracity lies in its stellar trails, long, looping streams of stars that arc around its core like ribbons of cosmic spit. These aren't graceful orbital paths, they're the shredded remains of smaller clusters, stretched into luminous tendrils by tidal forces as NGC 7622's gravity pulls them apart. The most striking example is a nearby globular cluster, now reduced to a smudge of stars being drawn into the cannibals' maw at over 100 kilometers per second. Spectroscopy reveals these captured stars have distinct chemical fingerprints, betraying their foreign origins like crumbs from a stolen meal. But the real shock came when astronomers mapped the cluster's core. Instead of a smooth distribution of stars, they found chaotic swirls, stellar populations with wildly different ages and compositions, layered like geological strata. This mishmash of stellar generations suggests NGC 7622 didn't grow through gentle mergers but through violent, repeated conquests, each digested cluster leaving behind a telltale imprint in the mix. Some stars orbit backward, others in steeply inclined planes, clear signs of multiple systems swallowed whole and still resisting assimilation. It's as if the cluster's history is written in the rebellious motions of its captives. The mechanics of this cosmic consumption are brutal. When a smaller cluster ventures too close, tidal forces peel away its outer stars first, creating the glowing streams we observe. As the victim's core plunges deeper, gravitational interactions with the cannibal's resident black holes and dense stellar populations heat it up, accelerating its disintegration. Within a few million years, a blink in cosmic time, the smaller cluster is reduced to a diffuse smear, its identity erased while its stars become anonymous citizens of the predator's sprawl. What makes this behavior extraordinary is its efficiency. Most large clusters grow by accreting gas or merging with peers of similar size, but NGC 7622 specializes in targeting victims 10 times smaller, a wolf hunting mice. This strategy allows it to grow steadily without the disruptive violence of equal mass mergers. The captured stars don't just add bulk, they bring fresh fuel as their gas-rich debris falls toward the cluster's center, potentially igniting new rounds of star formation. The implications ripple across astrophysics. If cannibalistic growth is common, it could explain why some supermassive star clusters appear older than their host galaxies. They've been feasting since the universe's youth, accumulating stars while others dissolve. It also reshapes our search for dark matter. The gravitational scars of these mergers could reveal how dark matter clumps around clusters, leaving subtle fingerprints in the trajectories of devoured stars. Yet the most haunting question remains unanswered. What happens when the cannibal runs out of prey? Simulations suggest it might turn inward, its own stellar populations becoming fuel for future growth through collisions and mergers. Or perhaps it will meet a rival of equal appetite, triggering a clash of titans that could reshape its galactic neighborhood. One thing's certain, the universe's largest structures don't grow peacefully. They take what they can, and NGC 7622 is the proof. Its stellar banquet a reminder that even in the vastness of space, nothing goes to waste. Deep in the cosmic desert of space, astronomers once spotted what appeared to be twin star clusters identical down to their stellar populations, their shapes, even the subtle patterns of dust weaving between their stars. But when researchers tried to measure their distances, the truth unraveled. These weren't siblings at all. They were the same cluster, duplicated and warped by an invisible cosmic funhouse mirror known as gravitational lensing. This is the Mirage Cluster, a celestial illusion so convincing, it fooled even the most seasoned observers into seeing double where only one existed. At the heart of this cosmic trickery lies Einstein's theory of relativity, which predicted that massive objects could bend light like a prism bending sunlight. When a dense galaxy or dark matter clump lies directly between us and a distant star cluster, its gravity distorts space-time so severely that the cluster's light takes multiple paths around the cosmic obstacle. Some rays curve left, others right, converging again at our telescopes as separate yet eerily similar images. The effect is like looking at a candle through the stem of a wineglass, watching its flame multiply into ghostly repetitions along the rim. The Mirage Cluster's most striking feature isn't just its duplicates but their mutations. Lensing doesn't merely copy the cluster, it stretches and squeezes its image like putty. One replica might appear as a smeared arc, another as a fragmented circle of starlight dubbed an Einstein ring. In extreme cases, the same star can appear in 5 places at once, its light split and reassembled by the lens's intricate gravitational field. Early astronomers, unaware of lensing, catalogued these warped reflections as distinct objects, only realizing their mistake when spectroscopic studies revealed identical chemical compositions and redshifts, a cosmic fingerprint proving they were viewing one cluster through a funhouse mirror. Yet the illusions don't stop at visuals. Lensing amplifies the cluster's light like a natural telescope, allowing astronomers to study details otherwise too faint to detect. Background stars, typically invisible, suddenly flare into view as their brightness gets boosted 100-fold. Transient events, supernova flares, appear delayed in some lensed images compared to others, their light taking longer cosmic detours around the lens. The Mirage Cluster thus becomes both a puzzle and a tool, its distortions encoding secrets about both the cluster itself and the invisible matter warping its image. What makes this phenomenon truly unsettling is its implications for cosmic cartography. If lensing can conjure phantom clusters from nothing, how many other objects in our sky are optical tricks? Current estimates suggest up to 10% of distant clusters could be lensed mirages, their true forms hidden behind layers of gravitational distortion. The Mirage Cluster isn't just a curiosity, it's a cautionary tale, reminding us that the universe delights in illusion and sometimes seeing isn't believing. Every warped image is both a deception and a revelation, hiding truths in plain sight while teaching us to question the reality of what we observe. Winding through the galactic outskirts like celestial rivers, stellar streams tell the silent story of violence that unfolded billions of years ago. These ethereal trails of stars stretched and torn by gravitational forces are all that remain of globular clusters that ventured too close to their host galaxy's tidal pull. Imagine a cosmic game of tug-of-war where gravity wins relentlessly, peeling stars away one by one until the cluster dissolves into a glowing filament arcing across the night sky. The most famous example, the GD1 stream, spans over 90 degrees across our view, a fossilized remnant of an ancient cluster whose stars now drift like breadcrumbs marking a path of destruction. What makes these streams so valuable isn't just their haunting beauty, but the forensic clues they hold. Unlike intact clusters where stars move in synchronized orbits, stellar streams preserve the gravitational history of their environment. Their twists, gaps, and density variations act like a cosmic seismograph, recording past encounters with dark matter clumps, dwarf galaxies, or even rogue black holes. The Palomar 5 stream, for instance, shows bizarre kinks and splintered branches, evidence it recently plowed through a massive but invisible dark matter substructure, its stars scattering like pins struck by a bowling ball we can't see. The real revelation lies in their chemistry. Stream stars often carry unique elemental signatures unusually low in metals like iron, revealing they formed in the early universe before supernova had enriched the cosmos with heavy elements. The C19 stream, discovered in 2021, contains stars with iron abundances just 1/5000th of the Sun's, making them the most chemically primitive stars ever found. These celestial fossils offer a direct window into the universe's first generations of stars, untouched by later pollution. But the ultimate surprise came when astronomers realized some streams don't trace back to clusters at all. The Phoenix stream in the southern hemisphere appears to be the corpse of an entirely different beast, a dwarf galaxy stripped so thoroughly, only this stellar tendril remains. Its stars rotate in alternating directions, a signature of galactic rather than cluster origins, suggesting our galaxy's halo might be woven with the remains of both consumed clusters and dismantled galaxies. These ghostly rivers are rewriting galactic archaeology. By mapping their paths, we've uncovered invisible structures like the Milky Way's long-dead Sausage Galaxy, whose collision left streams orbiting at steep angles to the disk. Others, like the Helmy stream, crisscross in chaotic loops, betraying our galaxy's turbulent merger history. Every faint streak of light is a chapter in a story we're only beginning to read, written in stars that outlived their homes to become cosmic storytellers. And as telescopes grow sharper, these streams promise even darker secrets, perhaps traces of primordial black holes, or the true distribution of dark matter written in the scars they carry across the sky. Inside the heart of the globular cluster Messier 4, two stars perform a cosmic ballet so intimate they defy the laws of stellar physics. Orbiting each other in a blistering 20-minute dance, these binary stars are separated by a distance smaller than the radius of our Sun, close enough that their outer atmospheres should have merged or torn each other apart billions of years ago. Yet here they are, spinning in defiance like celestial daredevils, untouched by the chaos of their crowded stellar neighborhood. This isn't just a rare oddity. It's a fundamental challenge to our understanding of how stars survive in the universe's most chaotic environments. The existence of such tight binaries in dense clusters was long considered impossible. Globular clusters are gravitational mosh pits where stars jostle and collide with relentless frequency. Simple probability dictates that close-knit pairs should be ripped apart by passing stars or absorbed into larger systems. Yet observations reveal these duos are shockingly common. In Omega Centauri alone, astronomers have catalogued dozens of binaries with orbits shorter than a single Earth day. Their survival hinges on a delicate balance. Their mutual gravity must be strong enough to resist external disruptions, yet gentle enough to prevent catastrophic mergers. How do they cheat destruction? One clue lies in their formation. Some tight binaries might originate as triple systems, where a close pair is shielded by a distant third star whose gravity deflects intruders like a cosmic bodyguard. Others could be the products of exchange reactions, where a lone star is captured by another during a close encounter, settling into an improbably tight orbit through gravitational bargaining. The most puzzling cases, though, are stars that seem to have spiraled inward over time, as if some unseen force is tightening their orbit like a winding clock spring. The implications ripple beyond mere curiosity. These binary systems are cosmic powerhouses, generating X-rays and gravitational waves as they interact. Some funnel material between them, creating accretion disks that glow with the heat of 1,000 suns. Others, if they contain neutron stars or black holes, could eventually collide in explosions detectable across the universe. Their very existence forces us to rewrite the rules of stellar dynamics. If stars can cling this tightly in the universe's most violent neighborhoods, what else have we underestimated about their resilience? Every impossibly close pair whispers a challenge not just to our models, but to our imagination, proving that even in the chaos of crowded space, stars find ways to hold on to one another against all odds. One of the most unsettling cosmic contradictions lurks in the constellation Cetus, a star cluster so defiant, it refuses to play by the universe's most fundamental rule. NGC 1052DF2, an enigmatic smudge of stars, shouldn't exist according to everything we know about gravity. This sprawling, ghostly gathering has a glaring absence where there should be an overwhelming presence: dark matter, the invisible glue thought to bind all cosmic structures together. Imagine building a skyscraper without steel beams, only to watch it stand tall against hurricane winds. That's the level of impossibility this cluster represents. What makes this discovery so revolutionary is how it flips the script on galaxy formation. For decades, astronomers believed dark matter acted as scaffolding for the visible universe, its gravitational pull shaping galaxies and clusters like an unseen hand molding clay. When researchers first measured the motions of stars in NGC 1052DF2, they expected to find the telltale signs of dark matter's grip, stars orbiting too fast to be held by visible matter alone. Instead, the stars moved sluggishly, their velocities perfectly explained by the meager gravitational pull of the cluster's visible stars and gas. Remove dark matter from the equation, and the numbers still add up, a cosmic heresy that sent shockwaves through astrophysics. The immediate assumption was that our instruments had failed. Perhaps intervening dust or measurement errors had skewed the data, but repeated observations with the Hubble Space Telescope and ground-based spectrographs confirmed the impossible. This cluster functions perfectly well without the mysterious substance that supposedly dominates the universe's mass. Even more baffling, the cluster isn't alone. Several other dark matter-less anomalies have since been spotted, including NGC 1052DF4 and the oddly diffuse KK3, each one a cosmic rebel thumbing its nose at conventional cosmology. Explanations range from the mundane to the extraordinary. One camp argues these clusters might be the aftermath of violent galactic collisions, where tidal forces ripped away not just stars but the surrounding dark matter halo like a cosmic peel being stripped from fruit. Supporting this, some simulations show dark matter can be separated from visible matter during high-speed encounters, leaving behind naked stellar aggregations. Others propose these clusters formed in rare pockets where dark matter was scarce from the beginning, like bubbles in a cosmic loaf of bread where the yeast didn't rise evenly. But the most radical theory suggests our understanding of gravity itself might be flawed. Modified Newtonian dynamics, or MUND, proposes that gravity behaves differently at low accelerations than Einstein's theory predicts, eliminating the need for dark matter entirely. While MUND remains controversial, clusters like NGC 1052DF2 provide tantalizing fuel for its proponents. If gravity operates unexpectedly in these environments, it could rewrite not just dark matter's role, but the very laws governing cosmic structure. Yet the plot thickens when you examine these clusters' stellar populations. They're peculiarly rich in ultra-diffuse galaxies, faint, sprawling systems with far fewer stars than typical galaxies of their size. Some researchers speculate this could hint at an unknown link between dark matter deficiency and star formation, where the absence of dark matter's gravitational pull somehow stifles stellar birth. Alternatively, these diffuse galaxies might be the remnants of disrupted systems, their stars too spread out to betray any lingering dark matter signature. The implications ripple far beyond academic debate. If dark matter can be absent in some structures, it challenges the assumption that it's uniformly distributed throughout the cosmos. This could mean our current maps of the universe's mass, based largely on dark matter's presumed omnipresence, contain glaring blind spots, even more intriguing. These anomalies might be the key to finally pinning down dark matter's true nature. If we can understand why it's missing here, we might finally grasp what it actually is. For now, these dark matter-less clusters stand as cosmic paradoxes, ghostly reminders that the universe still holds mysteries no theory can yet explain. Every observation peels back another layer, revealing not just gaps in our knowledge but potential cracks in the foundations of modern astrophysics. And as telescopes probe deeper into the void, one unsettling question lingers. Are these clusters flukes of nature or harbingers of a scientific revolution waiting in the wings? The answer could reshape our understanding of everything from galaxy formation to the fate of the cosmos itself. Imagine looking at a flock of birds and spotting one that flies backward, defying the unified motion of the group. That's the kind of cosmic rebellion astronomers have witnessed in star clusters, where certain stars streak across the sky in the exact opposite direction of their stellar siblings. These aren't just outliers, they're celestial renegades, rewriting the rules of how stars behave inside their gravitational families. Take the globular cluster Omega Centauri, where astronomers tracked a group of stars moving in tight, counter-rotating orbits, like cars driving the wrong way on a cosmic freeway. These rebels don't just drift slightly off course, their trajectories plunge through the cluster at steep angles, sometimes even perpendicular to the dominant flow. The most baffling part, their velocities suggest they shouldn't have lasted long in such a dense environment. Every close encounter with a neighboring star should have either corrected their path or ejected them entirely. Yet there they are, stubbornly carving their own routes through the chaos. So how do these stars defy gravity's expectations? One theory points to violent histories. Perhaps they were stolen from another cluster during a galactic collision, arriving with momentum so extreme the cluster's pull couldn't fully rein them in. Another possibility involves black holes lurking in the cluster's core. A close encounter with an invisible giant could slingshot a star into a bizarre orbit, like a pinball ricocheting off a hidden bumper. The strangest explanation, though, suggests these rebels might be survivors of binary systems torn apart by gravitational forces, their partners ejected entirely while they were flung onto these erratic new paths. But the real shock came when simulations revealed these rebellious orbits might be more common than we thought. In clusters like Messier 15, up to 20% of stars could be moving against the grain, not as lone anomalies, but as part of an invisible scaffolding shaped by the cluster's chaotic past. Some researchers now suspect these rebels are cosmic breadcrumbs, tracing paths back to ancient mergers or eruptions that scrambled the cluster's original structure. Others propose their evidence of dark matter's subtle influence, their odd motions betraying the gravitational tug of unseen mass clumped unevenly through the cluster. What's certain is that these stars force us to rethink how clusters evolve. Far from serene retirement homes, these stellar cities are dynamic battlegrounds where gravity and momentum wage endless war, and sometimes the stars themselves become the spoils of victory. Every rogue orbit is a reminder that even in the universe's most crowded neighborhoods, chaos still finds a way to leave its mark. The universe loves blurring lines, and nowhere is this more evident than in the cosmic gray zone where star clusters end and galaxies begin. For decades, astronomers assumed these categories were distinct. Clusters are dense balls of stars orbiting galaxies, while galaxies are sprawling systems with their own dark matter halos and complex structures. But then came the discoveries that shattered this tidy division. Objects so massive and complex, they defy classification. Take Omega Centauri, the Milky Way's largest globular cluster. With over 10 million stars, it outshines many dwarf galaxies. Yet what truly sets it apart is its chaotic mix of stellar ages and chemistries, something unheard of in typical clusters, where stars are uniform in composition. This anomaly led to a radical theory. Omega Centauri isn't a cluster at all, but the stripped core of a dwarf galaxy devoured by the Milky Way billions of years ago. The evidence: its stars orbit in multiple misaligned planes, a fingerprint of galactic ancestry, and its core hides an intermediate mass black hole, a relic of its former galactic heart. Then there's Male Roman II, a behemoth orbiting Andromeda. Twice as massive as Omega Centauri, it boasts its own retinue of globular clusters, a feature exclusive to galaxies. Yet it lacks the gas clouds and star-forming regions of even the tiniest galaxies, leaving astronomers scratching their heads. Is it a cluster that grew too big, or a galaxy that forgot to keep making stars? The answer might lie in its dark matter content, or rather, the lack thereof. Most galaxies swim in invisible dark matter halos, but Male Roman II motions suggest it's curiously light on this mysterious substance. This could mean it's a true hybrid, a cluster that ballooned to galactic proportions through sheer star count, without the dark scaffolding that defines true galaxies. But the plot thickens with ultra-compact dwarfs like M60 UCD1 in the Virgo cluster. These objects pack hundreds of millions of stars into spaces barely larger than a globular cluster. Their cores are so dense, stars are separated by mere light weeks close enough that alien civilizations there would see night skies ablaze with neighboring suns. Some UCDs harbor supermassive black holes far larger than expected for their size, suggesting they're the ravaged cores of galaxies stripped bare by tidal forces. Others, like the bizarre NGC 4546, are so enriched with heavy elements they must have formed from gas polluted by thousands of supernova, another galactic signature. The real kicker: these borderline objects might hold the key to one of astronomy's oldest questions. How do galaxies form in the first place? If certain clusters can grow massive enough to mimic galaxies, or if galaxies can be whittled down to resemble clusters, it suggests a continuum between these structures, shaped by environment and history rather than rigid categories. Every newly discovered hybrid forces us to reconsider our cosmic classifications, proving that nature doesn't care for human labels. It just builds, destroys, and rebuilds in an endless dance of gravity and time. Deep in the ancient stellar graveyards of globular clusters, some stars refuse to die, quietly defying the laws of physics to shine on long after their funeral should have been over. These are the zombie stars, celestial anomalies that keep burning through mechanisms so bizarre, they rewrite our understanding of stellar life cycles. Picture a corpse that not only sits up but dances. These stellar remnants radiate energy against all odds, as if cheating death itself. The most notorious zombies are white dwarfs that keep flaring back to life. Normally, these Earth-sized embers, the collapsed cores of dead stars, should cool into darkness over billions of years. Yet in clusters like Messier 13, astronomers have spotted white dwarfs flickering with erratic bursts of nuclear activity. One leading theory suggests these dead stars might be stealing hydrogen from nearby companions or interstellar gas, briefly reigniting fusion in their outer layers like a fire coaxed back to life with stolen kindling. The result, a star that technically died eons ago suddenly blazing as brightly as its living neighbors, its light masking its true undead nature. Then there are the pulsar zombies neutron stars that refuse to fade. These ultra-dense stellar corpses, born from supernova explosions, typically emit beams of radiation that slow over millennia as their rotation decays. But in clusters like NGC 6624, certain pulsars spin unnaturally fast, their energy signatures mysteriously reinvigorated. One explanation involves stellar cannibalism. If a passing star dumps fresh material onto the pulsar, the added mass can spin up its rotation like a top given an extra flick. Even more unsettling are the pulsars that emit gamma-ray flares centuries after their last visible energy source vanished, as if drawing power from some hidden reservoir. But the most baffling cases involve stars that glow without any conventional energy source at all. Take the Blue Straggler LP400 in NGC 188, a star that should have exhausted its fuel 12 billion years ago, yet burns with the vigor of a star 1/10 its age. Spectroscopic analysis reveals no signs of recent fuel theft or collisions. Instead, researchers speculate it might be tapping into exotic quantum processes or dark matter annihilation, deep in its core hypothetical mechanisms that could provide a slow but steady trickle of energy long after classical fusion ends. These cosmic revenants aren't just morbid curiosities, they're rewriting the rules of stellar retirement. Every zombie star discovered forces us to reconsider where we draw the line between life and death in the cosmos. Some might even hold clues to deeper mysteries like the potential for dark matter to influence stellar evolution or the existence of energy sources we've yet to imagine. As telescopes probe deeper into ancient clusters, one thing becomes clear. In the universe's oldest neighborhoods, death is never as final as it seems. At the heart of the globular cluster M22, astronomers found a gravitational monster that shouldn't exist, a black hole so massive it defies every rule about how these cosmic predators should grow. Dubbed the overmassive black hole, this behemoth weighs in at an astonishing 50,000 times the mass of our Sun, shattering the theoretical ceiling for black holes in star clusters. To put that in perspective, most stellar mass black holes in clusters top out around 20 solar masses formed from collapsing stars. Intermediate mass black holes, the next tier up, shouldn't exceed a few thousand solar masses in these environments. Yet here sits this colossal anomaly, lurking where models insist nothing so massive could form naturally. How does a black hole grow this big in a place with so little fuel? Traditional growth relies on a black hole voraciously consuming gas or merging with others over billions of years. But globular clusters like M22 are notoriously gas-poor stellar retirement homes where new material for feeding is scarce. One radical explanation suggests this black hole might be a primordial relic, forged in the chaotic aftermath of the Big Bang when extreme densities could have birthed black holes of any size. Another theory invokes a runaway chain reaction of mergers, where dozens of smaller black holes collided in the cluster's crowded core, snowballing into this single, unstoppable titan. The discovery sent shockwaves through astrophysics because it challenges the foundational hierarchy of black hole formation. We've long categorized them into neat bins: stellar mass black holes from dying stars, supermassive ones anchoring galaxies, and the elusive intermediates bridging the gap. This overmassive outlier blurs those lines, suggesting the universe has more flexibility and more violence in building these gravitational monsters than we ever imagined. Even stranger is the black hole's influence on its surroundings. Normally, a black hole this massive would dominate its cluster's dynamics, forcing nearby stars into tight, predictable orbits. Yet M22 stars move erratically, as if the black hole's gravity is somehow uneven like a magnet with patches of weaker and stronger pull. Some researchers speculate this could mean the black hole isn't alone. Perhaps it's part of a hidden binary system or surrounded by a swarm of smaller black holes that distort its gravitational fingerprint. Others wonder if we're seeing the aftermath of a near-miss collision with another cluster, an event so disruptive it left the black hole's influence permanently lopsided. The implications stretch far beyond M22. If overmassive black holes are possible in clusters, they could be the missing link in understanding how supermassive black holes form in galactic centers. Picture them as cosmic seeds growing through relentless mergers until they become the giants we see today. Or consider an even wilder possibility: these outliers might not be rare at all. Current detection methods could be missing others camouflaged in plain sight, their presence masked by the very clusters that host them. For now, this gravitational rebel stands as both a puzzle and a beacon, proof that the universe still holds surprises in its densest, oldest neighborhoods. And as telescopes peer deeper into other clusters, one question lingers: how many more of these rule breakers are out there, quietly rewriting astrophysics from the shadows? Buried behind thick curtains of cosmic dust in the constellation Serpens lies a celestial ghost, a star cluster so shrouded it's completely invisible to optical telescopes. This is the Invisible Cluster, officially catalogued as object name pending, a stellar gathering that only betrays its presence through the faint infrared glow of its heat. Imagine an entire city hidden behind a perpetual blizzard, its streetlights reduced to dim thermal signatures. That's the level of obscurity we're dealing with. While most clusters announce their presence with glittering arrays of visible stars, this one lurks in the shadows, revealed only because its star's warmth subtly warms the surrounding dust, emitting infrared radiation that pierces the veil. What makes this discovery so revolutionary is how it upends our search for stellar communities. Astronomers have long assumed that if a cluster were massive enough, its brightest stars would punch through obscuring material. But here, the dust is so dense, equivalent to stacking thousands of Earth atmospheres into each square inch of space, that even the cluster's most luminous giants are utterly smothered. The only reason we detected it at all was thanks to the James Webb Space Telescope's unprecedented infrared sensitivity, which captured the collective body heat of hundreds of stars shining at just a few hundred degrees above absolute zero. These aren't failed stars like brown dwarfs. They're fully fledged suns, their visible light completely absorbed and re-radiated as infrared by the intervening dust. The cluster's hidden nature raises tantalizing questions about its origins. Most star-forming regions are messy birthplaces, flinging gas and dust aside as newborn stars ignite. But this cluster seems to have retained its dusty cocoon unusually long, perhaps because it formed in an abnormally dense molecular cloud that hasn't yet been blown clear. Spectroscopic analysis reveals another oddity. The stars here are richer in heavy elements like carbon and silicon than typical clusters of their age. This suggests the dust shrouding them isn't just interstellar material. It's stardust literal, ejected by previous generations of stars that lived and died in this same region, their remains becoming the very veil that now hides their successors. The implications stretch beyond this one ghostly cluster. If such heavily obscured structures are common, we might be missing a significant fraction of the universe's stellar populations. Current surveys could be underestimating star formation rates in dust-rich galaxies, especially in the early universe when such environments were more prevalent. There's even speculation that the Invisible Cluster might represent a transitional phase, a brief window where young clusters remain veiled before stellar winds and radiation finally clear their surroundings. Supporting this, some models predict that up to 20% of clusters could spend their first 100 million years in near-total obscurity. Yet the most intriguing possibility involves rogue planets. Hidden within this dusty shroud, free-floating worlds could far outnumber the stars themselves, shielded from the harsh radiation that typically strips their atmospheres in exposed clusters. Some might even retain thick, heat-trapping atmospheres that make them detectable through their own infrared signatures, dark, wandering orbs warmed by internal heat rather than starlight. It's a reminder that the universe's hidden corners often hold the most surprising residents, waiting for the right technology to reveal their secrets. As telescopes like Webb peer deeper into these cosmic blind spots, one thing becomes clear. Our maps of the stellar neighborhood are still riddled with voids, not empty spaces, but uncharted territories hiding in plain sight. The invisible cluster isn't just an anomaly, it's a preview of the countless other shadows that might flicker to life in our data, rewriting what we thought we knew about where and how stars choose to gather. Deep in the constellation Aura, astronomers have uncovered a cosmic time machine, a star cluster that seems to be playing by its own rules when it comes to aging. Known as NGC 6397, this globular cluster defies expectations with stars that appear to be racing through their life cycles at nearly twice the expected rate, as if some unseen hand pressed fast forward on stellar evolution. While most clusters of its age, roughly 12 billion years, should be filled with sedate red giants and cooling white dwarfs, this one crackles with surprising activity, its stars burning through their fuel reserves like marathon runners sprinting the final mile. The first clue came from subtle irregularities in the cluster's color magnitude diagram, a tool astronomers use to chart stellar life cycles. Instead of the predictable curve of aging stars, NGC 6397's diagram showed a puzzling excess of blue hook stars, hot, helium-burning anomalies that should have transitioned to cooler phases billions of years earlier. These stars aren't just outliers, they dominate the cluster's upper ranks, glowing with a youthful intensity that contradicts their advanced age. It's as if an entire retirement community suddenly started training for the Olympics, their vitality inexplicably restored. What's driving this accelerated aging? One leading theory involves the cluster's extreme density. Packed tighter than most globulars, NGC 6397's core is a gravitational pressure cooker where stars jostle like commuters in a crowded subway. Frequent close encounters could be stripping outer layers from red giants prematurely, exposing their helium cores and effectively resetting their evolutionary clocks. Another possibility hinges on chemical pollution. The cluster might be saturated with extra carbon and oxygen from ancient supernova, altering how its stars burn fuel. Like a candle spiked with accelerant, these stars consume their nuclear resources faster under altered internal conditions. But the plot thickens when you examine the cluster's dynamics. Unlike typical globulars, where stars orbit in predictable patterns, NGC 6397's motions are chaotic, with groups of stars swirling in opposing directions. This turbulence suggests a violent past, perhaps a near-miss collision with another cluster or the Milky Way's disk that stirred the cluster's depths like a spoon in a coffee cup. Such an upheaval could have triggered waves of stellar collisions, creating hybrid stars with fresh fuel supplies that burn hotter and brighter than their untouched counterparts. The implications ripple far beyond this one cluster. If stars can age non-uniformly based on their environment, it challenges our ability to date cosmic structures accurately. Current methods rely heavily on comparing observed stellar populations to standard evolutionary models. But what if those models need rewriting? NGC 6397 hints that factors like crowding, chemical enrichment, and gravitational shocks might warp stellar life cycles in ways we're only beginning to grasp. Perhaps most intriguing is the cluster's potential as a dark matter laboratory. Some simulations suggest its erratic stellar motions could be influenced by an uneven distribution of dark matter, clumped in ways that selectively accelerate certain stars' evolution. If true, studying these fast-forwarded stars might offer indirect clues about dark matter's behavior in dense environments, a tantalizing prospect for solving one of astrophysics' greatest mysteries. As telescopes probe deeper into NGC 6397's anomalies, one truth becomes clear. The universe's clock doesn't tick uniformly. In its most crowded neighborhoods, stars can live and die by rules we're still deciphering, their lifespans rewritten by the chaos of cosmic companionship. Every unusual glow from this cluster is a challenge to our models, a reminder that time itself bends to gravity's whims in ways we've yet to fully understand. The universe loves throwing magnetic curveballs, and few are as baffling as the star clusters that crackle with magnetic fields strong enough to warp space itself. These magnetic mystery clusters, like the strange NGC 1261, don't just have magnetic fields, they're wrapped in cosmic force fields so intense they can redirect charged particles across light years and twist the trajectories of nearby stars. Picture a storm where the lightning doesn't flicker but hangs frozen in the sky, shaping everything around it. That's the level of magnetic dominance we're talking about. What makes these fields so perplexing is their sheer strength. Typical star clusters have weak, patchy magnetism leftovers from the interstellar gas that birthed them. But in clusters like Messier 5, the field isn't just present. It's a unified, galaxy-scale web that blankets the entire structure, measuring up to 100 microgauss, 10 times stronger than expected. That's enough to sculpt the paths of cosmic rays and even influence how stars move within the cluster. The real puzzle: these fields don't weaken over time like they should. Magnetic fields naturally decay unless something actively sustains them. Yet these clusters maintain their magnetic grip for billions of years, defying entropy like cosmic perpetual motion machines. So where does this relentless magnetism come from? One theory points to the cluster's neutron stars spinning stellar corpses that act like cosmic dynamos. As these ultra-dense objects rotate, their conductive interiors could generate enormous currents, turning the entire cluster into a giant circuit. Another possibility involves dark matter, with some exotic particles theorized to interact electromagnetically under rare conditions. If dark matter clumps in these clusters carry even a faint charge, their collective motion might weave invisible magnetic threads through the stellar population. But the most electrifying clue comes from the field structure. In NGC 1261, the magnetic lines aren't chaotic, they spiral outward from the core like a cosmic whirlpool, suggesting a central engine. Could a hidden intermediate mass black hole be powering this phenomenon? Its accretion disk acting like a colossal Faraday generator? Or are we seeing the aftermath of ancient supernova, their explosions so perfectly aligned that their magnetic shockwaves stacked into a lasting lattice? The implications stretch beyond astrophysics. If clusters can sustain such powerful fields, they might be cosmic particle accelerators on a scale we've never imagined, places where magnetic forces hurl electrons to near light speeds, generating gamma rays and neutrinos detectable across the universe. These clusters could even serve as natural laboratories for testing theories of quantum magnetism, offering glimpses into physics normally accessible only in extreme lab conditions. Every twisted magnetic line is a whisper from the universe, challenging us to rethink how invisible forces shape the cosmos, and proving that even in the quietest corners of space, magnetism can write its own rules. Hidden in the ancient glow of globular clusters, astronomers have uncovered a celestial jackpot, the Coronary Borealis stars, a rare breed of stellar oddities that could finally bridge the gap between how small and massive stars evolve. These aren't your average suns, they're cosmic chameleons, flickering between states like a light bulb with a faulty switch, and their bizarre behavior might hold the key to solving one of astrophysics' most stubborn puzzles: how certain stars cheat death by essentially rewriting their own expiration dates. What makes these stars so extraordinary is their chemistry, or rather, their shocking lack of it. While most stars are rich in elements like hydrogen and helium, our Coronary Borealis stars are nearly devoid of hydrogen altogether, as if someone scrubbed away their outer layers to expose the raw helium burning beneath. Picture a fruit peeled down to its core, its sweet flesh stripped away to reveal the tough, fibrous center. That's the kind of stellar anatomy we're dealing with here. This hydrogen famine should make them cosmic dead-enders destined to fizzle out quickly. Yet against all odds, they burn brighter and longer than models predict, glowing like stellar zombies that refuse to die. The leading theory: these stars are the products of catastrophic collisions, cosmic mergers where two white dwarfs, the dense husks of dead stars, smash together and reignite like a phoenix rising from the ashes. When a helium-rich white dwarf collides with a carbon-oxygen sibling, the resulting hybrid star doesn't just combine their masses, it triggers a nuclear renaissance, restarting fusion in a way that defies standard stellar life cycles. It's as if two retirees suddenly fused into a hyperactive teenager, burning through borrowed time with reckless abandon. But here's where the plot twists. These stars don't just defy aging, they also vomit carbon onto their surfaces in violent outbursts, temporarily dimming their light as soot-like particles cloud their atmospheres. In the cluster Omega Centauri, astronomers observed one such star suddenly dim by a factor of 100 in mere weeks, only to brighten again months later like a cosmic convalescent. This erratic behavior mirrors another mysterious class of stars, the Blue Stragglers, hinting that both might be different outcomes of the same underlying process, stellar resurrection through violence. The implications ripple far beyond these oddballs. If mergers can reboot a star's life cycle, it means globular clusters, once thought to be sterile retirement homes, are actually dynamic laboratories where stars cheat death through gravitational teamwork. Every R Coronii Borealis star is a living fossil, offering a glimpse into the universe's most extreme stellar makeovers. And as telescopes uncover more of these missing links, one thing becomes clear: the cosmos has a flair for second acts, rewriting its own rules in the crowded dance halls of ancient star clusters. Streaking through the cosmic void like a lost ship in an endless ocean, the runaway globular cluster HVGC1 slingshotted out of its home galaxy at speeds that defy comprehension, nearly 2,000 kilometers per second. This isn't just a cluster drifting leisurely through space. It's a celestial fugitive flung so violently that it crossed the distance from Earth to the Moon in under 2 minutes. The forces required to eject an object weighing millions of suns are almost unimaginable, yet here it is, barreling through the intergalactic darkness with no galaxy to call home. The story of HVGC1 reads like a gravitational thriller. Nestled in the massive galaxy M87, part of the Virgo cluster, this globular cluster once orbited peacefully alongside thousands of others. Then catastrophe struck. Simulations suggest a close encounter with not one, but two supermassive black holes. The titanic duo anchoring M87's core sent the cluster spiraling outward like a stone from a cosmic slingshot. The dance of these black holes, each weighing billions of solar masses, created a gravitational vortex so extreme, it hurled HVGC1 past escape velocity, dooming it to an eternity of exile. But here's what's truly astonishing: the cluster survived the ordeal intact. Most structures subjected to such violence would disintegrate, their stars scattering like dust in the wind. Yet HVGC1's gravitational bonds held firm, its core remaining densely packed even as it fled. This resilience hints at an invisible scaffold, perhaps a halo of dark matter, acting like cosmic Kevlar to shield the cluster from tidal disintegration. Or maybe the cluster was unusually dense from birth, its stars so tightly knit that not even a black hole's wrath could tear them apart. The implications of this discovery rewrite the rules of cosmic escape. If globular clusters can be ejected whole, galaxies might be seeding the intergalactic void with rogue stellar cities far more often than we thought. These castaways could become oases in the barren expanse between galaxies, their stars providing rare anchor points for wayward planets or even hypothetical life. Some might eventually be captured by other galaxies, becoming interstellar immigrants with chemical fingerprints betraying their foreign origins. Yet the most haunting question remains: where is HVGC1 headed? Unlike hypervelocity stars, which eventually slow due to interstellar drag, this cluster's immense mass means it could coast indefinitely, crossing the unfathomable gulf between galaxy clusters over billions of years. Future civilizations in distant star systems might gaze up to see its glittering sprawl dominating their night sky, a ghostly reminder of the violent forces sculpting the cosmos, and proof that even the universe's grandest structures aren't immune to exile. Tucked away in the constellation Hydra lies a cosmic relic so pristine, it's like stumbling upon an untouched tomb from the dawn of time. The star cluster NGC 4833 doesn't just contain ancient stars, it's a chemical fossil, a preserved snapshot of the universe's raw ingredients before generations of supernova polluted the cosmos with heavier elements. Unlike most clusters where stars show signs of enrichment from stellar explosions, this one's chemistry is eerily pure, nearly devoid of elements like iron, carbon, and oxygen, as if frozen in the first few 100 million years after the Big Bang. Picture opening a vial of air from Earth's earliest atmosphere. That's the level of preservation we're talking about. What makes this cluster so extraordinary is its defiance of cosmic recycling. Most celestial objects are built from recycled material, gas and dust laced with the remnants of dead stars. But NGC 4833's stars formed from primordial hydrogen and helium so uncontaminated, their spectra resemble theoretical models of the universe's first stellar generation. They're the astronomical equivalent of a prehistoric insect trapped in amber, offering a direct line to conditions we've only simulated in supercomputers. Even the cluster's structure is archaic, loosely bound and asymmetrical, unlike the dense globular clusters that dominate our galaxy's halo, suggesting it's a rare survivor from an era before gravity perfected the art of stellar organization. But the real treasure lies in the cluster's lithium content. This lightweight element forged in the Big Bang is notoriously fragile, destroyed easily in stellar cores. Yet here, lithium persists in abundances that match predictions of the early universe's composition. It's like finding an unbroken seal on an ancient jar, confirming that no astrophysical process has tampered with the contents. This single detail alone helps astronomers calibrate models of cosmic nucleosynthesis, the process that created the universe's first atoms. The implications ripple far beyond astronomy textbooks. If clusters like this were common in the early universe, they might have been the nurseries where the first population Roman 3 stars, hypothetical, massive stars made purely of hydrogen and helium, lived and died. Their supernova would have seeded the cosmos with heavier elements, yet we've never directly observed one. NGC 4833 could be the bridge between that mythical first generation and the metal-rich stars we see today. Yet the mystery deepens when you ask how this cluster stayed so pristine. Most ancient structures were polluted over time by mergers or interstellar winds. One theory suggests it formed in a galactic backwater, a quiet corner where few supernova ever reached. Another posits that it's a captured fragment of a dwarf galaxy so small, it never had the stellar density to trigger extensive chemical recycling. Whatever the reason, its existence forces us to reconsider how efficiently the early universe mixed its materials, and how many other untouched time capsules might still lurk in the cosmic shadows. For astronomers, this cluster isn't just a curiosity, it's a Rosetta Stone. Every photon from its stars carries clues about the universe's chemical infancy, helping us decode how we went from a soup of simple atoms to the complex elements that build planets, life, and even the device you're using right now. And as telescopes grow more sensitive, the hunt for similar fossils intensifies, because each one could rewrite another line in the story of how the cosmos learned to build itself. In the vast stellar tapestry of the cosmos, some discoveries don't just challenge theories, they mock them outright. Enter the impossible cluster, an unassuming gathering of stars catalogued as VVVCL002, nestled in the galactic bulge of the Milky Way. By all known rules of astrophysics, this cluster shouldn't exist. Its stars move in orbits so chaotic, its structure so unstable, that simulations show it should have torn itself apart within a few million years. Yet here it stands, defiantly intact for over 10 billion years, like a sandcastle surviving hurricane after hurricane without a single grain out of place. The first clue to its impossibility lies in its location. VVVCL002 orbits perilously close to the supermassive black hole at our galaxy's center, a region where tidal forces are so extreme they shred molecular clouds before stars can form. Imagine trying to light a candle in a wind tunnel. That's the level of futility star formation faces here. Yet against all odds, this cluster's stars not only formed but endured, their gravitational bonds resisting the black hole's relentless pull. Spectroscopic analysis reveals even more baffling details. The stars exhibit a near-perfect equilibrium of masses, as if some cosmic sculptor carefully arranged them to cancel out each other's instabilities. What truly flummoxes theorists is the cluster's lack of dark matter. While most globular clusters rely on this invisible glue to stabilize their structures, VVVCL002 stellar motions match predictions based solely on visible mass. It's like watching a house of cards remain standing during an earthquake without the cards touching the table. One radical explanation suggests the cluster might be the remnant of a dwarf galaxy stripped bare by the Milky Way's gravity. Its dark matter halo peeled away like an onion's layers, leaving only the stars behind. But even this theory struggles to explain how such a fragile arrangement survives in the galaxy's most violent neighborhood. The plot thickens when you examine the stars themselves. Unlike typical clusters where stars share a common birth, VVVCL002 hosts multiple generations with drastically different chemistries. Some are ancient metal-poor relics, while others shine with the heavy element richness of much younger stars. This disparity hints at a history of repeated replenishment, as if the cluster somehow attracted new stellar members long after its formation, despite the hostile environment. One provocative idea posits that the black hole's gravity might actually funnel wandering stars into the cluster's embrace, a cosmic game of gravitational pinball where losses somehow become gains. The implications are staggering. If clusters can form and persist in such extreme conditions, it forces us to reconsider where and how we search for stellar communities. Current models might be underestimating the resilience of gravitational bonds, or perhaps missing entirely new mechanisms that allow stars to cooperate under duress. Every flicker of light from this defiant cluster is a dare to astrophysics. Rewrite your rules or explain why they don't apply here. And as telescopes probe deeper into galactic cores, one unsettling question lingers: how many other impossibilities are we overlooking, simply because we didn't think to look? From celestial vampires and runaway black holes to diamond-filled stars and ghostly dark matter voids, the past 50 discoveries have shattered our cosmic rulebook. These star clusters aren't just glittering ornaments in the night sky, they're cosmic rebels, defying gravity, time, and even the laws of physics as we know them. Take the Phoenix cluster birthing stars in a galactic furnace that should sterilize all life, or Omega Centauri's hypervelocity fugitives fleeing at speeds that mock gravity's grasp. Then there's NGC 1052DF2, the cluster that exists without dark matter, like a skyscraper standing tall without steel beams. Each one of these enigmas forces us to confront an uncomfortable truth. The universe is far stranger, far more inventive than our textbooks ever dared to suggest. What's truly humbling is how these discoveries expose the limits of human imagination. For centuries, we've mapped the cosmos assuming it adheres to tidy patterns, only to find star clusters teeming with impossible phenomena. Blue stragglers that cheat death, tidal tails stretching like cosmic taffy, and pulsars that devour their companions in slow-motion feasts. These aren't exceptions. They're proof that the universe thrives on chaos, rewriting its own rules in crowded stellar cities where gravity plays by nobody's playbook. Even our language falters in the face of such wonders. How do you define a star when some glow for billions of years without fusion, or a black hole when they fling entire clusters into the void like cosmic slingshots? Yet for all we've uncovered, these 50 mysteries are merely the first page in a saga still unfolding. Imagine what else lurks undetected. Clusters woven from dark matter alone, stellar orphans drifting between galaxies, or even ancient relics from before the first stars ignited. With every technological leap from James Webb's infrared eyes to gravitational wave detectors, we peel back another layer of the cosmic onion only to find more questions. That's the thrill of exploration, the knowledge that out there, hidden in plain sight, are truths we haven't even thought to question yet. So the next time you gaze at a star cluster, remember, you're not just seeing points of light. You're looking at a frontier where every flicker holds a story waiting to upend everything we thought